Good morning, everyone. Very nice to see you. Thanks for inviting me here today. So, yeah, conscious that it's Wednesday, the last day of the school, 9 o'clock. You're probably out partying last night. So, I'm going to start easy. So, the first part of the presentation is much more general about the kind of the problem space that we're in, and then we'll get to the QAOA stuff in the second part. So for those who are only, the hardcore quantum people who are like, that's all I'm here for, you just have to, grin and bear it through the first part. But for the rest of you, hopefully you find the background information kind of interesting and kind of puts this, problem that we're solving into context. Okay, so, just a little bit about me. I'm British. I actually many years ago, did a PhD in physics. So I know a little bit, or at least I used to. It was a while ago. Right now, I live in Gothenburg, and I'm the head of software development for Jeppeson's crew and aircraft scheduling products. And we are actually world leading in this area, and it maybe is hard to understand. But if you've been on a commercial aircraft, with the crew flying you somewhere, British Airways, KLM, Lufthansa, pretty much you name it, very likely the crew on that flight was planned by the software that we build in Gothenburg. So, small world. All right, Jeppesen. Let's just give a little bit of what's that? It's a company. We are in a very innovative industry, the aviation industry. This is Wright brothers' first flight in December 1903, so just over 100 years ago. And of course, a lot has happened since that famous flight. Jeppesen, who gives the name to our company, he was an early pilot. He got his pilot's license signed by one of the Wright brothers. He was a mail delivery pilot, and he started out making little maps because it was a very, very dangerous business flying in those days. People got lost and crashed and died. And you can see here, out of 18 pilots flying on this particular route, 4 were killed in 1930. And so he started making these little maps, and he said, I started making these maps not to make any money, but to stay alive. But of course, when other pilots found out, they were interested, and they were like, we want to get a copy of these maps. So he started making copies and selling them. And that was how Jeppesen started in the aviation map business. And of course, today, aviation maps look a little bit different. If you think Google Maps are complicated, you should see what it looks like up there. It looks very clean when you look up, but if you look at the actual airspace maps, it's really complicated. Jeppesen was, of course, printing all these maps, and in 2007, this is what it would have looked like in Jeppesen HQ. All of these reams and reams of paper that had to be printed and then delivered in big suitcases to the aircraft. And think about it, every single aircraft in the world has to have a set of these charts, and they need to be up to date, right? If you're flying a plane, you don't want to be flying on an old map that doesn't show that radio mast they just built as you're coming into land. That's not good. Now, of course, this was 2007, and then something happened. You can probably guess what. And then everything went digital, and Jeppesen was suddenly faced with, transforming from a printing company into being a software company. Now, this is kind of all by and by, because in Gothenburg we don't do charts. We actually work with airline, crew, and aircraft planning solutions. So we're a little bit of a subset. We were actually an acquisition of Jeppesen back in around 2006. So we work with, assigning aircraft and assigning crew to flights. And if you get that wrong, you can end up on the front page of the news. Here's an example from a few years ago. American Airlines got their, planning for their captains wrong around Christmas time, and they realized they had 15,000 flights that didn't have a captain. And that's not going to result in happy passengers, especially around Christmas time. That usually ends up with you having to phone people up and promise them extra money to work overtime, etc. And that's usually very expensive and also not necessarily very popular. This was not our software, by the way. You can't see that here, but this is competition's software. So, all right, we're about 400 people in Gothenburg, many different nationalities. We like to have fun, and we love solving very large and complex problems, which improve the quality of life for people everywhere. Yeah, and we think air transportation is a big enough, complex enough problem to do that. If you look at the air transportation network, you can see it's pretty complicated. This transports around 4 billion people a year. So how did it get that way? Again, we're just warming up for those of you who wanted to get to the quantum part. We're just warming up, but how did we get to 4 billion plus people a year? Well, as you can see over there, very small amount of air traffic in 1950, but pretty much, what you might describe as exponential growth ever since. And what's interesting, I think, on this chart is that there's a lot of different bumps, like the oil crisis, the Gulf crisis, and it really maybe sometimes makes a very small dent in that growth. 9/11 probably made the biggest dent, but then it kind of resumed its relentless climb up there. 2008, the world recession and the Lehman Brothers, etc. Also only a small dent. Of course, something else happened after that, but we'll get to that in a second. Just for fun, this is just for fun. For those of you who want to sort of get geeky on the aviation stuff, you see charts like this, and it says revenue passenger kilometer. Okay, what the heck is that? These are really simple things. So in the airline industry, if you take one aircraft seat and fly it 1 kilometer, you generate one available seat kilometer, one ask. And if you have a paying passenger sitting in that seat and you fly them 1 kilometer, you generate one revenue passenger kilometer. So as an example here, if you take a 200-seat aircraft and fly it 1,000 kilometers and it has 140 people on board, you can calculate the ask. That's the seats times the distance, so that's 200,000. But the RPK, that's number of passengers times the distance, so that's 140,000. So these are just simple industry things that you don't need to know, but just kind of fun because you might see graphs if you ever read, industry papers that mention things, or read Bloomberg or whatever, talk about revenue passenger kilometers. And okay, now I know what that is. All right, though COVID came along. All right, that was that was a big setback. This was what people were expecting it to do, but would it return to that? Well, now, of course, now we're past COVID. So we have the figures in here. Now, here we see the big drop after COVID, really huge. I mean, from a baseline, it's been baselined at 100 there, and it's gone down to, like 90% basically drop in the traffic. Now, of course, it has recovered since then. So that's for those who work in the aviation industry, that's reassuring. Yeah, and we can also calculate things like passenger load factor then. To see that passenger load factors have recovered. Here you just take the RPK and divide it by the ASK, which you now know how to calculate. So you can calculate load factors. Of course, calculating load factors for one flight is easy. You just divide passengers by the number of seats. But this is when you do it for more complex things. All right. But what load factor is your airline profitable? Well, around 75% is a good rule of thumb. This is actually slightly pre-COVID, but COVID, as you know, it's kind of disrupted things. Things are getting back to normal, but around 75%. So the first 75% of the tickets you sell on your flight, they're just covering your costs. And it's only the rest that you sell after that that's actually going to make you any money as an airline. Good to think about if you're thinking of starting an airline. Right, yeah, which reminds me of the joke. I don't know if you heard the joke. How do you become a millionaire in the aviation industry? You start an airline as a billionaire. Think about it. All right. All right. Where does the money go? Direct operating costs, about 50%. Ground operating costs, 30%. System operating costs, 20%. And salaries, let's look at salaries. So, these are very approximate numbers, but if you just put in these approximations, 100,000 for a pilot, dollars, 50,000 for a flight attendant, you multiply your airline number of pilots, number of cabin crew, you get really big numbers. So if you can save an airline, 1% of their crew costs, just 1%, you're talking about millions of dollars a year. And typically, we as a company in Gothenburg can show savings to airlines of around 2 to 5%. So we can really justify helping them to save millions of dollars. And that's why they buy our software, of course. So Delta, like 180 million passengers a year. And if you look at their route, it would look very much like a big mess. And of course, one thing that it might remind you of is, the traveling salesman problem. I'm sure you're all familiar with it, but just in case, you're a salesman, you have to visit every city and get back home. And this works by you pick one city, and after your home city, so you have n-1 choices, and then you can go to the next city, you have n-2 choices left, and so on and so forth. So you generate a factorial, and then since you can go in either direction, you divide by 2. And for 35 cities, you get a big number because it's a factorial, of course. And the point is that this grows very, very fast with the number of cities. All right, so this is the kind of problems that we're solving. Now, we're not solving exactly traveling salesmen, but we're solving, for example, tail assignment. So here we have the problem of many flights and many aircraft, and then we need to decide which aircraft is going to operate which flight. So these are all 3-letter abbreviation codes for airports. So, for example, DEN, that's Denver. SFO, that's San Francisco. For example, SAN is San Diego, and so on and so forth. So, it's like, okay, if we're flying from San Francisco to Denver on flight 250, which aircraft is gonna fly that? And it's called tail assignment because, as you can see in this photograph, at the back of every airplane, it has a unique tail identifier. So that number that's printed on the tail of the aircraft there, that is unique for every airplane and identifies it. So once you've assigned that number to the flight, you know which airplane is going to fly. And these are some of the benefits that you can get if you do this in a smart way. You have increased aircraft utilization. Aircraft are very expensive. Resources, so you want them up flying. You don't want them sitting around on the tarmac. You can, if you do it smart, you can reduce your maintenance costs. You can burn less fuel. And when you do that together with your crew planning, you can have more stability because, for example, when the aircraft lands, maybe the crew stays with the aircraft and take off again, rather than having to run across to the other side of the airport, jump on another plane that may be late arriving. All right. So a set of flights operating in sequence by the same aircraft is called a route. That important concept, because we'll be coming back to that when we get to the quantum part. In order for the route to be considered legal to operate, it has to fulfill a number of constraints. You can't just take all these things and stick them together and say you're done, right? There's a lot of things you have to consider. So, for example, when a flight arrives at an airport and it's going to take, the same aircraft's going to take off again, you have to do things like, as you know, take the luggage off, take the passengers off, put new fuel in. That creates a delay, or a turn time, as we call it. And when we're planning, we have to have a minimum turn time. So you can't have an aircraft that lands and then 1 minute later takes off again. That's not going to be considered feasible. So that you're going to have a minimum turn time restriction. You're going to have to, make sure that when you do your route planning, that the aircraft is on the ground for at least the minimum turn time. Then you have destination restrictions. Some aircraft are more noisy than others, and some airports are more noise sensitive than others. So you might have a restriction that this airplane cannot fly to that airport. Sometimes you have curfew restrictions, which are similar, but they're time-based. This noisy aircraft cannot fly to that airport after that time in the evening. And you have maintenance constraints. You cannot just fly your airplanes around continuously. You have very rigorous, as we're all happy for, maintenance checks that say, and there's, just like you have with your car, we have different service intervals, have the same thing with airplanes. All right, you need to build them in. Now let's just have a look at some of the sizes of the problems that we face in the real world. So let's look at the really big airlines. You can order them by the number of aircraft that they have, in which case you'll find Delta is at the top. They have 979 aircraft, at least they did in February, when I pulled these numbers out of Wikipedia. But yeah, you can see that it's like a few American airlines at the top. and then some Chinese ones, etc. But if you look instead at number of routes served, it's a slightly different picture. Now we see Southwest is at the top, serving 3,000 routes, and then Ryanair actually next with 2,500 roughly, and so on and so forth. And Delta only actually shows up then number 6. So, who's the biggest depends on how you do the measurements. Anyway, but just to give you a feeling for the kind, when we're talking about aircraft and routes, what are the kind of numbers that we're talking about? We're talking about hundreds of aircraft and thousands of routes, basically. And this is what an actual solution can look like for the tail assignment problem. Each of these rows is for one aircraft. If you could squint and see, it's maybe hard to read, but if you looked over in the very, very far left, you'll see the tail number of the aircraft. So that's just showing that this is this row is that aircraft. Each green vertical line is a flight. And then you have other activities of maintenance and other stuff shown in. But just to give you an idea for what kind of generating there. This is how it fits in to the bigger picture with the commercial airlines. So we have years out, we need to fix the fleet structure, and we need to do what's called manpower planning. We create our timetable, we assign the fleets, and then we do a bunch of other stuff in terms of planning the crew, which tends to be just a few weeks before. And then also pretty much on the day, we do something called fleet recovery and crew tracking. This is basically repairing any issues that come up on the day, like a crew member calls in sick, or an aircraft has to go for unplanned maintenance, and then you need to, you need to recover your schedule in a good way. Just very quickly over some of the crew part. It's not going to be the focus for today, but just to give you a little taste for some of the things that you need to do when running an airline. Manpower planning over there on the left. This is really what helps you answer questions like you're expanding your fleet. How many people do you need to hire? You can't just go and hire a bunch of 787 captains or A380 captains off the street. You won't find them hanging around. So you need to plan and train people, and this can take months and years. And so you need a strategic plan to do that, and that's what manpower helps you with. And also, if the scenario is the opposite, suddenly demand drops and you need to put some crew on furlough. Okay, how many crew should I put on furlough? All of them? No, that's not going to work. But exactly how many? This is what manpower planning can help. Crew pairing. That's kind of similar to the tail assignment problem, but we're now doing it with people instead. But similar problem, you have all these flights and you need to do it in 2 steps. First, you need to connect them together into what are called these pairings. So we just join the flights together into, like little beads on a necklace, each of these flights, and they have the property that it starts and ends at the home base. So crew are different to aircraft because aircraft don't really care where they stop at the end of the day, whereas crew members tend to like to come home to their family. So when we plan crew, we have to be more sensitive to get them home. Sometimes they can, of course, overnight in a hotel, but the aircraft, they don't really have a home to care about. So it's a little bit different problem in that sense. All right, we can just very quickly look at an example. Here's a few flights. Again, this is a lot of similarities between crew and aircraft. So here is Denver to Chicago, Chicago to San Francisco, San Francisco to Seattle, etc., etc. Okay, so here's our flights, and then we need to build them up into this pairing. So here's the first flight in the morning, going out from Denver to Chicago. And then we're going to add the next one. Now we're going to San Francisco, and then Seattle, then to San Diego, and now back to our home base. So now we've made our pairing. Crew member can wake up in Denver, fly this route, and come back home again in the evening, and they're happy and they've flown those 5 flights during the day. So this is what these crew pairings look like in real life. You can see that some are 1-day pairings, on the Monday, but we have 2-day pairings, 3-day pairings, and typically a 5-day pairing is about the longest that you'd make. After that, people tend to get a bit homesick. All right, and then of course there's rules to follow as well. When we do this, government rules, airline rules, union rules, We have to, like, when it's the crew, at least, we need to take into account their preferences, their quality of life. Alertness is one factor. So we actually have a model for how awake the crew member is. And if we plan in a bad way, we end up with a lot of um, flights where the crew are actually having a low alertness. They're feeling a bit fatigued. But if we do it in a smart way, we can cover the same flights with the same crew, but there's no crew who are having a low alertness. Again, this is all just background stuff. Here's just for a little bit more background. Here's an airline rule, and you can just see it starts to get quite complicated about how much rest you can have and when and so on and so forth. All right, we're back to the traveling salesman problem. Want to just explain, I think you're all probably very familiar with this, but these problems take enormously long time to solve by brute force. That's kind of like the way not to do it. This is from a textbook on optimization theory. They're just showing that for if an operation takes 10 to the minus 13 seconds, then if it's growing linearly as a problem, then well, you can still solve 100,000 in 10 to the minus 8 seconds. But if it's growing as a factorial like traveling salesman, then already at 100 cities, you're at 10 to the power 137 years. And to put that in perspective, that's long. The universe is 10 to the 9 years old. So that's way longer than the age of the universe. And that's just on 100 cities. And we saw already that we had, thousands of routes to cover. So obviously, brute force isn't going to work. Fortunately, classical optimization has, made some good progress in this. This is just showing how traveling salesmen's evolved over time. We had algorithms for classical optimization in the 1940s. And back in 54, we could solve traveling salesmen for 49 cities. 87, 532, 1998, 13,509. Now, since we're in Sweden, we know that there's an optimal tour. If you're planning your summer vacation next year, this is the route to take. You see 24,978 cities. But we haven't stopped there as humans. We got bored solving, flat traveling salesman problem. This is the biggest traveling salesman problem I know. It's like 119,614 stars. Solved to optimality, so this is guaranteed the shortest route you can take between all those stars. Of course, it would take a long time to do it in practice, but it's nice to know that there are solutions out there. Now, I think the point of this is that we've gone from here 49 cities in really just like a few decades to solving 119,614 stars. Our point is that today's challenging problems are going to become trivial in the future. So we have to think big. Now, interestingly, we don't necessarily have to solve things to optimality. This is a traveling salesman problem for 1.33 billion stars. It's not solved to optimality, but it is solved within, as you can see here, 1.0038 of the possible shortest path. So it's close to theoretical optimum. And sometimes that's good enough. And methods to find a good solution can be a lot faster. We like to talk about 3 dimensions of optimization: solution time, solution quality, model accuracy. When we're solving optimization problems in the real world, we want to find a feasible solution as quickly as possible. And we favor solution time over quality. Why? We want to check that we're solving the right problem. We want to get an answer out as quickly as possible to see that, yeah, we're on the right track. Then we can work to find a better solution. So find a solution, check that you're on the right track, and then make it better. And keep doing that until you run out of time. So that typically means that if you have a cost graph, that you'll initially find a solution with a high cost, but then you can improve that, reducing the cost until eventually you find it gets harder and harder to lower the cost. And that means that when you plot that out on time as a result of your computer runs, that you end up with a graph like this. So these are very typical optimization runs. This is the time to an initial solution, and this is the time available that we maybe have to find a solution. So again, depending on what problem you're looking at, the time available can be very sensitive. If you're in a major aircraft, hurricane, the airport is closed, and then all the aircraft are scattered around the world, and then the weather clears. Okay, now we need to get you home. It's no good if someone says, I'm going to have the optimal solution for you in a week's time. It's like, no, I want to go home tomorrow. So we need to find solutions in appropriate timeframes. All right, and of course we don't know what the optimal solution is always. Here's some real examples, original and new methods. And you can see here that, the original gets us some initial solutions quickly, but the new method is getting us better solutions in the long run. So now we might want to look at how we could fuse these together so we can get good initial answers and better answers long run as well. All right, we're getting towards quantum stuff. So why is quantum interesting then? Well, here's a chart from Gartner, and they've kind of said, okay, number of logical qubits, it's a log scale, but as time goes by and these number of qubits become available for us, what are the kind of problems that we can solve? And I'm sure if you're into quantum cryptography, you've heard about RSA being cracked, and they're saying that might not happen till 2045 or something like that. But at the same time, protect your secrets now with post-quantum cryptography so that people don't steal them now and crack them later. But from our point of view, what was interesting is that root optimization is called out, 2033. Okay, about 10 years out. That's a rough guess. But at least it's on the chart and it's not decades and decades away. So the point then here is that we're really interested in solving these currently unsolvable optimization problems. This picture here represents optimization problems. The stars in the inner circle, they represent optimization problems that we can solve pretty much exactly. Like 49 cities in the traveling salesman. We can get that exact solution. Then the ones in the next ring, the blue ones, they're ones we cannot solve to optimality. Like the 1.5 billion stars, we can maybe get close. And then the other stars out here, there are problems that we cannot solve at all today. And of course, what we're interested in is using new techniques to expand the rings so that things that were previously impossible move into the possible, and we can start to do useful things with that. Now, kind of things we'd like to do with, in airlines is to have continuous and holistic optimization and recovery, where we're solving for crew and aircraft all the time, and we're able to generate, through a digital twin, a view of the future. So it's kind of a little bit like weather forecasting. What's the airspace congestion over New York going to look like in 4 hours' time? What's the impact of the weather in London going to be in 6 hours' time? Take all of those things into account and continuously optimize it for all the different factors in that big network that we showed at the beginning. We can't do that today, but we think through new technology, and quantum's definitely one of the ones that we're interested in, these kind of things can become possible in the future. All right, so this kind of, sorry for the long intro, but this kind of builds us up to our cooperation with VACT, which we were in from the beginning in this cooperation. Here are 3 of our experts who partnered with VACT. Matthias there, he's our lead optimization scientist in Sweden. And yeah, so we start with the quantum approximate optimization algorithm. I think you learned about this earlier in this course. I'm not going to spend too much time on it, but then imagine we can represent our optimization problem as a quantum Hamiltonian, which we'll call HP, and then we're going to encode the ground state in the wave function psi. So that would be nice if we could do that. Now, of course, that's not so easy, and it might be that we can only create the ground state, initial ground state psi I, for some much easier quantum Hamiltonian. So, okay, we can't, we have our desired Hamiltonian HP, but we don't know how to create the wave function the ground state for that, but we do know how to do it for an easier Hamiltonian H0. So let's get started with that. And then we'll use this concept of, adiabatic optimization, which means that we'll start with our easy Hamiltonian H0, right? And then we'll very, very slowly and very, very gradually evolve it over to our desired Hamiltonian. And at that point, it will actually mean that our wave function now represents the problem that we're trying to solve. And we can do that, through this time parameter. It's not hard to see that, when we put t equal to 0 into our equation here, that this term becomes H0 and this one drops out. And when we put small t equal to big T, then this term drops out and we have just this one left. So that's nice. Now, of course, we need to do a little bit of mathematical trickery. So we're going to use the Lie product formula because we have this sum here, but we can approximate that with this product. We just need to apply it n times. So this is how we end up with our QAOA algorithm. So we have, just summarizing some of the key actors then in QAOA. We have our easy starting point, so I. We have our cost Hamiltonian, which was what we want to solve. We need to have this mixed Hamiltonian with the key feature that it doesn't commute with our cost Hamiltonian. Because remember, we're going to do this thing iteratively, and iteratively means we need to apply it step by step by step. And if everything commutes, then we can't really have steps. So we need something that doesn't commute to sort of make it possible to have these discrete steps. And then we have these angle parameters. So here's QAOA. Here's the formula. We have our initial wave function over on the right, and then we apply, our, it's basically that adiabatic formula, but we've used the Trotter formula to split it into these to this product of operators, and if we apply that a sufficient number of times, we're going to have that adiabatic evolution towards our desired state. Right. So sometimes it's easier to represent these things visually. So we picture it as our initial state with the green box. We apply our operator, one level of operation with these angle functions, gamma 1 and beta 1. If we just did it once, that would be it, and then we could measure. Of course, that won't give us a very satisfactory answer, but it's the simplest one. And then, of course, we actually build that up into P levels. So we start with our initial, we apply with gamma 1, beta 1, we apply again gamma 2, beta 2, so on and so on until we've done it P times. Now we can measure. All right, so that's QAOA. I think you've been exposed to that before, so hopefully that was a quick reminder and made some sense. You could connect things together there. How do we go from Taylor-Simon, our industrial problem, to quantum approximate optimization algorithm? Well, we need to follow a few steps. So we start with our industrial problem. So that's Taylor-Simon. All right, we've seen that. Very good. We know all about that now. Now we need to model and simplify. All right, so you saw a lot of the complexity that was there with the rules and the constraints and all of those things. It makes it tricky. We're gonna apply some simplifications. First, let's get a mathematical model for the problem for the Taylor-Simon problem. So here's the mathematical modeling. It always, when you first see it, can look a bit confusing, but it's actually really simple. It just captures the basics in mathematical notation. So here is the set, R is the set of all possible aircraft routes. So that's fine. We have to sum over all of those. And then we have this variable XR, which is a binary decision variable. So it basically means it's a 0 if we don't do it, and it's 1 if we do it. And then CR is the cost of using route R. So let's just pause there and see, does this make sense? So we're saying that we're going to sum up over all the routes R that exist in the possible set of routes big R with these binary decision variables, which means it's 0 if we don't use it, and it's 1 if we do use it. And CR is the cost of that route. So we're basically saying let's sum up the roots that the cost of all the roots that we're using, and ignore the cost of the roots that we're not using. And the binary decision variable is what throws away the ones we're not using and keeps the ones that we are using. That makes sense? Good. All right. And then, we have the set of flights F. And again, we have a 1 if this flight is in the route and 0 otherwise. This is basically giving us the constraints that we don't sort of use aircraft on 2 flights at the same time, for example. So these are really just modeling the constraints that we've talked about. Right, now we're going to map it to a known computer science problem. All right, let's just have a look here at how we can see routes as set partitioning. So here's our set, and then we do a very simple set of 10 flights. Now we're going to apply set partitioning. So we partition that set into 3 subsets. And you can see the subsets at the bottom there. And now we've generated three pairings or 3 routes. And you can calculate the cost then of each of those routes. Now, of course, there are very many possible routes. So in the work that we've done with quantum, we're actually going to make things a little bit easier. Remember, we're on this journey from the industrial problem that we're trying to solve, Taylor-Simon, to getting some numbers out with quantum computing. So with the number of flights, number of aircraft, the number of possible routes gets to be very big, right? So we're actually going to artificially limit that. So we're going to look at some legal routes that have been generated, and we're going to just pick a subset of those. And then we're also going to make sure that in that subset, we've got the solution so that we don't end up searching that space for something that's not there. So we're cheating a little bit, but at the same time, I mean, it's still useful, right? Because we're basically saying instead of searching this big problem space, we're just reducing it a little bit. We're giving it a little bit of a helping hand. But it's still a challenging problem to solve. All right, so now we've gone from set partitioning to exact cover problem, which is very similar, of course. But now it looks like this. Let's say that we've chosen 40 routes, and we've got, in this particular case, 471 or 472 flights actually. So what we do, we create a little table, and we say, okay, which flights are in which route? So the route 0 at the top there, that includes includes what we call flight 1, whereas route 1 includes flight 4, and so on. So it's basically a fairly sparse matrix. And then our challenge then is to select rows from this matrix, right? Which rows are we going to pick? And we want to make sure that we don't have the same flight in more than one row. Okay, so let's see, we've picked route 11 there, and that has got flight 2 in it. You can see that. But if we were to pick the one below, route 13, which has also got flight 2 in it, that wouldn't be any good because we can't have the same flight in the same route. That airplane needs to be in one of these routes and not the other. Right. So we can figure out, we can find a solution, with that covers exactly once these things. All right. So then, just to show how that's represented as a solution, this would be the ground state. So what we would do, solving this quantum-wise, we would have 1 qubit for each route. So with 40 routes, we'd have 40 qubits. And then the ground state would be the solution, and it would be a 0 if we use the route, and a 0 if we don't use the route, and a 1 if we do use the route. And we start here and we go, in this particular case, we go from right to the left. So this is route 0. So that doesn't, we're not going to use that one. The first one that we actually use is actually route 11, which is shown by the blue line there, and that's actually shown by that one there. And then we use root 15, and we're going to use root 38. Yeah, so I think hopefully you get the idea there that we generate this matrix. It's filled in with these ones and zeros, and then our challenge is to find the best selection of these routes that include, that doesn't include the flights more than once in each. Right, good. Sorry for all the waffle. Now we can represent these things in a graph notation as well. So we have one node being a route, and then we use an edge to indicate that that route shares a flight with another route. So these are, again, just examples, but here you see an example from 8 routes, and you can see that some of these routes share flights and some don't. So for example, over here there's no connection between those 2 nodes, so they're not sharing a flight, whereas this node shares flights with a few. All right, and it also shows that the problem size isn't just limited to the size in terms of the number of routes. So in this case, we have a problem with 15 routes, which is much more connected. There's much more sharing of flights between the routes than the 25 routes. So that actually might be a more tricky problem to solve because you've got more overlaps. The less overlaps, usually, the easier it is to find a solution. Less problems to solve. Okay, so we're on this journey. We started with our industrial problem, Taylor-Simon. We've modeled it. You saw the maths for that. Now we've converted it over to an exact cover problem. What's next? All right, well, the next problem is to then convert that problem to a quantum Ising formulation so we can use the Hamiltonian. All right, now you might think, oh, no, that's going to be tricky. How am I going to do that? Well, the really nice thing is that since these classical optimization problems are very common, well known, someone's done all the hard work for us. So you can basically go and look up how to do that. Here's an example. Here is a paper by Andrew Lucas, which explains, here's the Ising formulation for many NP problems. So you can basically just go in there and say, okay, this is how that particular, NP complete problem, whatever, in math is expressed as a quantum Hamiltonian. So good. So that's possible. So now we've able to use this Ising formulation, and now we've got it into a Hamiltonian form, and now we can use QAOA to solve that. So we stick it on a computer, and we of course don't know what these angle parameters are, so we need to optimize those. That optimization typically happens on a classical computer, so we're actually running hybrid. And this is, again, something that we've done as part of our work with VACT, and there's a paper on this where you can read much more of the nitty-gritty technical details. But here's some of the results. So again, you actually saw these routes earlier. We did 8 route with 8 qubits, 15 routes with 15 qubits, and 25 routes with 25 qubits. These are, of course, not on real qubits. We didn't have access to real qubits. We had to simulate it. But you can see that this is the number of iterations of the QAOA, and that's basically the probability of finding the optimal solution. So, after about a dozen iterations, you can solve the 8 route one, the 25 route one wasn't far behind. Remember, the 15 route one was the more complicated one with more dense nodes there. So that was a little bit more tricky, but we've done that. This was appreciated and actually made the news back in 23 that we were solving a real logistics optimization problem. Of course, we're not done. I mean, there's many more things to worry about. Introducing more levels means there's more parameters to optimize, and we have the effective noise, of course. So that doesn't make things easier. So we did some simulations with noise as well. We've also done some stuff with quantum annealing on D waves, similar kind of stuff. And there's another paper on that if you're interested. This is the list of publications, which is available in the slide deck. For those who find this interesting and want to go and learn more about it. But yeah, basically that's where I am today. Summary: we have really ambitious optimization goals for the future. We have a lot of interesting problems we want to solve that we can't solve with current compute capabilities. We like quantum computing because it's a disruptive form of computing. That is a definite potential to get us to where we want to be. People are predicting that root optimization, the kind of problems we're solving, will significantly benefit through quantum in the next 10 years. Maybe hybrid, we don't know, but we're definitely really interested in that. We picked Taylor assignment because it was perhaps the easiest to model for our work with VACT. And as you saw, we're still really only solving toy versions, but we expect to make good progress on this. So in short, we're really excited about the future and the kind of problems that we'll be able to solve in the coming years. So that's it. Thanks.
Thank you very much. Super interesting. It's already a question.
Yes, so I noticed that you were basically using like pretty much all-to-all connectivity, or each of the nodes had an equal number of neighbors in the examples that you looked at. How would that change if you went for, let's say, a more realistic example, such as, let's say, a hub and spoke model, as most airlines actually tend to use? Would that be simpler, more complicated? How does that end up working out?
That's a good question. Yeah, hub and spoke is more common in US, and it's perhaps not so common, not as common perhaps in other parts of the world. I think, to be honest, we don't really know how that would play out. So we'd be saying that we'd probably have to actually run to see what the outcome would be. So we haven't looked at that, basically, is the summary. But it's a good thought.
Thank you.
Maybe you're interested in doing some work with us. We'll see if we can find an answer to that one. Okay. Good.
We have questions coming in online as well. How many qubits and depth do you need to solve a real-life problem?
Yeah, no, that's good. I would say we would probably need in the order of hundreds of qubits to solve a real-life problem.
In the order of 100.
Yeah.
Okay, another question. How fast could it be compared to current GPU on HPC?
Well, of course, those are the kind of techniques that we're using today, and we can get good solutions to very large problems fairly quickly. So I think it's basically how where do we think that we're going to start to win in terms of speed? Again, it's going to come back to when we get to hundreds of qubits, we're going to start to break even on these. But I think the answer is, we'll probably be solving different, more ambitious problems. So we won't be sort of comparing apples with apples. It's going to be a little bit tricky. But yeah, I mean, at some point, the quantum computer is going to win, and we're going to be able to solve the problems that we solve today with GPUs faster. And that's just going to get faster with time. Again, it's some of that stuff depends on exactly what problem you're solving. I don't know if that was a good answer or not, but
thanks. Any other questions?
Yeah.
More?
Hi, thank you for a very nice presentation. I know that you now have a new industry PhD starting at Jeppesen. So what are some of the problems that you will investigate with it?
That's a really good question. We're still discussing that, actually. So obviously, there's more work to be done in this space. But I think there are other possibilities as well. So we're right now going through those opportunities, but hopefully we'll let you know soon. Yeah. Right. Yes, down the front.
Thank you for a nice presentation. So I have some experience in quantum machine learning, and I know that there are different ways of solving the Ising model using quantum neural network states.
Right.
Have you tried that once? This is
No,
by Taylor.
no, we'd love to do that. Maybe that's something Albert can do.
Yeah, I have a master student. I think
Yeah.
he likes to do this stuff. So I
Okay.
can probably try to connect it to.
Yeah, no, we have not looked at that. So I mean, there's so many opportunities, I would say, in this space. So we're excited.
Great.
But yeah, please send me a note.
Yeah, thanks.
Great. This is what we want to see.
Yeah, absolutely.
Collaborations being formed on the spot. Anything else from the room?
Okay. If not, then you're always welcome to contact me through email or otherwise. I'm on LinkedIn as well. But thanks again for having me here. It's been a pleasure. And let's. I know you're going to continue this now with some getting your hands dirty. I'm looking forward to see what happens next.
Yeah, indeed. Okay, thanks again.
All right, thank you.
Perfect. Okay, thank you for that introduction. So, and thank you, Peter, for the very nice introduction to the tail assignment problem. So now it's time to get our hands nitty-gritty and dirty by going into details on how we actually can solve this tail assignment problem on a quantum computer, showing you the workflow step by step on how you can solve a combinatorial optimization problem like the tail assignment problem on a quantum computer. So therefore, this talk has an accompanying notebook. And if you want to follow along in this notebook, you can download the notebook from this GitHub webpage. It's github.com/vikstall/autumn-school-cas 2024. And then you just click on this notebook right here. So that gives you the link to the notebook, which you can download by clicking here, download the raw file. Now I have it on my computer. And then you can go to lumi.csc.fi. And then you can just choose to upload that notebook so that we later on can run a small toy example on the Lumi quantum computer. So let's give it 30 more seconds for everyone to have time to set up their notebooks and follow along.
Let's make this abundantly clear also for our online participants. You share the link to the notebook. So people open that URL, and then they also go to notebooks.csc.fi.
Yes, you can run that notebook directly on your computer, but there's an extra part in this tutorial where we actually solve a small toy problem on the Lumi quantum computer, and then we need to be running it from the Helmi server cluster. Okay, so how many of you in here have been able to download and set up the notebook? 1, 2, 3, 4. Okay, I think
I'm thinking about the notebooks, notebooks.cc. So is Modupe here? Do we have access to that? Yeah, so lumi.cc.fi that's the open on demand platform that we're using. So I'm not sure if all participants have access to the notebooks actually, but they do have access to the open on demand.
So when you set up this course notebook, is there a different like project environment? You can choose like your user environment, or it's like a project.
This is a
Can you one of these? Let me see.
Sorry for the echo. We're working on it.
No, I have no audio here.
Testing. I think it's fine now. Yeah.
Okay.
Pointers is actually on lumi.csc.fi, not on notebooks, so it's fine. Yes, like Pointers is actually using lumi.csc.fi, using Lumi open on demand, so it's fine to use Lumi.
Okay, perfect. I hope every one of you have got your notebook set up. So let's begin with a short recap of the tail assignment problem that Peter has already introduced. So in the tail assignment problem, we have the task of assigning aircraft identified by a number on their tails to scheduled flights while minimizing operational costs such as maintenance and other constraints. So let's look at a toy problem here. So as input to our problem, we are given a set of aircraft that are assigned a set of flights. These aircrafts are therefore also called routes, since they are flying a set of flights. So in this case, we have that route number 1 flights the flight to Arlanda and Gothenburg. And we have route number 3 flying from Arlanda and Helsinki. So this particular graph here to the right can be encoded into a constraint matrix here on the left, describing all the connections, all the flights that the routes are connected to. So for example, the first column here, we see that we have a 1 if route number 1 flight Arlanda, and 1 because it also flies flight Gothenburg, but 0 since it doesn't fly Helsinki. And for all these routes and aircrafts, we also have an associated cost with operating them as well. So mathematically, we can formulate this problem as minimizing the cost of all routes, where this x here is a binary decision variable, indicating if we are to include our route R in our solution or not. But we should minimize this cost function such that this very important constraint is satisfied. And this mathematical constraint equation says that each flight should only be operated by one route, since having more routes or aircraft flying the same flight is very costly. So this is a very important constraint to satisfy. Now, in this toy problem, you can maybe guess what the solution is. And the solution for this problem would be to picking route 1 and route 4. Because we see that they have flights that land on distinct nodes in the flight set here. So there are no two routes sharing the same So this would be the solution for this very simplified tail assignment problem. Now, for this tutorial that we're going to look at today, the instances that have been generated only have one feasible solution per data instance. That means that this minimization function, that's only relevant if you have multiple solutions that satisfy this constraint. Once you have multiple solutions that satisfy this constraint, you want to find which of the solutions also minimizes your cost function the most. But since we only have one feasible solution, we can ignore this minimization part and only focus on the constraint part. Therefore, we can rewrite this mathematical expression also as a matrix vector equation, where A here encodes our constraint matrix for the problem. X is a vector with where each element is a binary decision variable, and 1 is a column vector of ones. So let's go to the notebook and load in our problem. So here in cell 1 is where we load a problem. So this particular problem that we loaded consists of 77 flights and 8 routes. We therefore have 8 decision variables that we need to find. So if we plot this A matrix, this is our input data to the problem. Now we are looking for a binary vector x that when multiplied with this matrix gives us a column vector of only ones. And just by looking at it like this, it would be impossible to find it just with your eye to see what the solution is. Okay, so what's the next step for solving this problem now on a quantum computer using QAOA? So the first step is that we need to do some reformulation of our original problem to put it as a cost function, or more particularly on QBO form, which I will explain more in the next slide. But essentially, we want to put our problem on a cost function such that our binary vector are mapped to real scalar values using this cost function. And then once we have our cost function on QBO form, we can represent the QBO problem as a Hamiltonian, where the Hamiltonian encodes the solution to our problem in its ground state. Then we can use QAOA, which is a parameterized quantum circuit, to create quantum states that represents solutions to our problem. So let's see how the tail assignment problem can be mapped to QBO. So QBO stands for quadratic unconstrained binary optimization. And this involves notation change where the optimization problem is represented on the following form. So we have a cost function f of x, which we should minimize over all binary vectors x. And Q is a n by n matrix that now encodes the problem in a new representation. So let's see how the tail assignment can be put on QBO form. So we begin with our mathematical formulation of the tail assignment problem. What we do next is that we subtract 1 from both sides of the equation and then square it using the scalar inner product This will thus be 0 if and only if there exists a solution vector x that evaluates this to 0. So we can write this as a cost function now that minimizes over all possible binary vectors ax minus 1 squared. So to recapitulate, in this form, a solution will exist if and only if there exists a binary vector x such that this function, when evaluated using this binary vector, is 0. And if no solution exists, all possible binary vectors will result in a cost that is larger than 0. So we now have we have now expressed the tail assignment problem as a cost function, but it's not on the cubo form yet. So to do that, we just expand the square using the scalar product rule. And the first term, we see that it's in the correct cubo form. And the scalar, this last term here, is just a scalar value, and it doesn't contribute to the optimization itself, so that we can just throw away. And then we have a linear term here as well, and that actually corresponds to the diagonal elements of this matrix Q, which we can see by expanding Q in its summation form, like this. So we can write it as a sum over diagonal elements and non-diagonal elements. And since for the diagonal elements, since xi are binary variables, we have that xi times xi equals xi. Therefore, this linear term, when written in summation form, is this, which with some mathematical clever can be shown to be written as this expression, where diag is simply making this vector into a diagonal matrix. Yeah, so our Q for the tail assignment problem becomes this here. So now that we have written our classical optimization problem on the cubo form, it's time to express it as a quantum Hamiltonian. So the way we do that is simply by a substitution of variables. So we want to go from binary variables 0 and 1 to spin variables that are either -1 and 1. And that we do just using this simple substitution. And if we plug that in, we see that we go from something to this to something to this, which kind of looks like a Ising Hamiltonian. So the last step is simply to promote your spin variables to Pauli Z matrices, and you thus have your cost Hamiltonian, whose ground state hopefully encodes the solution to your problem. Okay, so let's go back to the tutorial and calculate Q. So here we compute Q for the tail assignment problem. And next, we reformulate the cubo expression to a Hamiltonian by doing this variable substitution. And this also gives us a new variable called B, which corresponds to the linear terms here, and B will itself depend on Q. So now it's time to generate our Hamiltonian. That we do using this function. This generates the terms in the Hamiltonian. So if we run this cell, we see that all of these strings with Pauli said corresponds to the different terms in our Hamiltonian. And the coefficients here are the corresponding weights for each term in our Hamiltonian. Okay, the next step, now that we have found the Hamiltonian that we want to optimize, we can use the QAUA algorithm to do it. And in Qiskit nowadays, it's very easy to create a QAUA circuit. You just import this QAUA ansatz with your cost Hamiltonian and specifying how many layers do you want to run. In this case, we choose 2 layers. And right now, when we plot the circuit, it just looks like this black box function. But when we later on transpile it to a backend, we will see how this black box function will actually be implemented on an actual quantum computer. So the next step is to take this black box function and transpile it onto our hardware or our backend. And this can involve several things, such as picking out the subset of qubits on your chip that are the best. So you run your algorithm on those particularly qubits that perform the best. You can include stuff like error suppression and also routing of your qubits. So in this first part of the demonstration, we will just use a simulator backend. But hopefully in the end, we will use the actual Lumi quantum computer. So here we define our backend as a simulator backend, but it could be also a real quantum computer backend that you define here. Then you need to generate a path manager or a transpilation that transpiles your circuit given your backend. And when we do this, we now see that the QAUA circuit now looks like this long thing. So it's a some 2-qubit ZZ gates and also some single qubit gates. Okay, so now it's time to execute the QAUA circuit and optimize the angles with respect to the expectation value of our post Hamiltonian. So for this, we need to start with some initial guess for our parameters, for our classical optimizers to start from. So we initialize our parameters. Since we're doing 2 layers, we have in total 4 parameters, gamma 1, beta 1, gamma 2, beta 2 to optimize. Yeah, and next we create our cost function that we can input to a SciPy minimizer to minimize this cost function with respect to the angles gamma and beta. So this cost function estimator takes in the variational parameters. It takes in the quantum circuit, the QAUA circuit, the observable that we want to estimate, in our case, the cost Hamiltonian, and also a Qiskit primitive called the estimator. An estimator is used for computing expectation values in Qiskit. So here we define our estimator with our given backend. and we run SciPy minimize of our cost function estimator that we defined up here for our given initial parameters, and we choose a standard Kobula optimizer. SciPy have many different optimizers that you can try out, but this one seemed to work particularly good for this problem. Did I forget to run a cell? Probably this one. Okay, so it says that the optimization was successful. And if we plot the expectation value or the cost function for the number of different iterations, we see that the optimizer is able to minimize the expectation value of our cost Hamiltonian. So, as final part now, it's time to run the QAUA circuit once more using the optimal parameters that our classical optimizer have given us. So here's the final circuit with the optimized parameters from the classical optimizer. And this time, we are now using the sampler primitive in Qiskit, since we only want to sample from the output state of our QAUA circuit. So we only want to sample the bit strings from the end of our QAUA circuit now. And hopefully, we have prepared our QAUA circuit in such a way that the solution state will have a very high overlap with the state that QAUA prepares. So if we run the sampler now for the optimized circuit, we can see the outcome of all possible binary strings that was sampled. And these are, I have normalized the number of shots per bit string over the total number of shots. So this corresponds to the probability of obtaining this particular bit string. So it had like a 0.4% probability that this bit string was observed. Okay, and now we need to do some post-processing to return the result in classical format. And this involves filtering the solutions to see if any of the sampled bit string from our optimized circuit actually satisfy the constraints of our original problem, which was this cost function here. So if any of the sampled bit strings from our final output gives 0, then we have found a solution. So now here we loop over all sampled bit strings that we found, and if the classical cost function is evaluated to 0, then a solution is found. And it says a valid solution is found, and this is the corresponding bit string that solves the tail assignment problem. And then we can also look at which is the most likely bit string to be sampled from this final QAUA output state. And if we look at that, we see that the most likely bit string happens to also be the solution bit string in this case. And the most likely bit string in this case has a 28.5% probability of being sampled. And this can be compared to random guessing, where the probability of obtaining the solution in this case would simply be 1 over 2 to the power of number of roots that you have. And in this problem, we have 8 roots. So that would be simply 0.2 0.4%. So with QAUA, we have increased the likelihood by quite a lot of finding the optimal bit string. Then, just for fun, we can also plot a histogram over the classical cost function f of x over all observed bit strings and see what is the likelihood that we find a certain cost. And the purple one here is the cost corresponding to the optimal solution. And we see that it is much higher than all other faulty solutions. Okay, so this was all done on a simulator. Let's see how it works on an actual quantum computer and what we can learn by doing that. So now we will load a smaller 2-qubit and 2-flight instance to fit on the Lumi 5-qubit quantum computer. And we do the same thing by computing what our Q is and what our B for the Ising Hamiltonian is. So this is our cost function, or our cost Hamiltonian in this case. We have 2 terms and 2 weights for the terms. In this case, again, we do 2 layers of QAUA. And first, let's look at how this problem works on a simulated backend, and then we can compare the performance between the simulated backend and the real backend and see how noise might disturb some things. Okay, and in this case, I have pre-calculated the actual optimal parameters for this particular problem. So we skip the classical optimization because I have done that beforehand. So we just input the optimal parameters to our circuit directly. And this is the final circuit. So now we just run sampler. We sample output strings from this circuit. So we run this circuit 4,000 times and look what counts we get. And if we normalize the counts, we see that the state 0, 1 is returned deterministically in this case with 100% probability. And if we look here, it also is that 0, 1 is the solution to this problem. So for this particular problem with 2 layers of QAUA, it could deterministically with 100% probability give you the correct state to your problem. And here's just a histogram. Okay, and now let's run the same thing, but on the Helmi quantum computer. So we load up the Helmi module backend. And then we first transpile the circuit, given our new Helmi backend. And then we optimize single qubit gates. And this is the corresponding quantum circuit that would be run on the Helmi quantum computer. So this I ran yesterday. So let's see how it will change today. But for the Helmi quantum computer, it returned the correct state, which was 0, 1, with about 70% probability. While there was some error here where it returned 1, 1 with 30% probability. And it seems to be that, I don't know, this first bit has a lot of bit flip errors, maybe. But let's see how it goes today. So we submit our job. It says job is queued. I don't know. Usually this takes maybe a minute to run.
So while that is running, do you know which qubit you're running on? So it's qubit 3 and qubit, which one?
I don't know. I just know it's the middle qubit is one of them, of course. I don't know about how the qubits are labeled here compared to the topology that you showed us the other day.
Yes, that's why there's like, I mean, maybe not now, but later I could show you how you can ensure you're on using, you know which qubit you're using.
Yeah.
By, you know, manually having the qubit registers, and then there's the initial layout function in Qiskit. So once you have that, you can be sure that, okay, I'm not running anything too stupid, for example.
Okay.
Yeah.
So with that, I can transpile my circuit onto the best 2 qubits.
Yes.
Let's see, what's the job status? Went really fast this morning. But anyway, so this, we can just have a look at this picture meanwhile. So this shows the problem that we face with errors, how it decreases our performance of the algorithm. But yes, that was everything I had to present. Thank you very much for listening.
Let's take some questions until job status gives us output.
Yeah, VTTQX is a bit down at the moment. We are facing some issues, so that could be the case. We are actively dealing with it, so sorry for the inconvenience,
Yeah,
but
no problem.
you can always try running on the fake backend. Oh, okay, that's good.
Is yours done? And how does this bar? So it looks almost the same for you. 57, okay. And just know that when we ran this problem on the Chalmers 2-qubit device, we managed to get up to 97%. But that was a lot of hand. I mean, you can optimize this circuit a bit more by hand as well. Did any questions show up in the chat?
Not yet. I asked them whether...
Yeah, someone got 1-1 with 98, but that's the wrong answer. It's confidently incorrect.
So if you go to the optimized circuit,
for the Helmy,
yeah, that should, no, the circuit before this, that should only have 2 CZ gates. And then I think you're ending up with 4.
Yeah, and the reason for this is that these are rotational CC gates. So these rotational CC gates need to be decomposed into 2 CZ gates with a RZ gate in the middle, like shown here. You have 2 CZ gates with a RZ gate in the middle.
And are these like symmetric somehow? Like if you end up doing RZ with the negative phase on the first one, on qubit 2 instead of with the positive phase on qubit 4, are they identical? Maybe up to some global phase?
You mean if I could move this one here, up here to this qubit?
Yeah, just as a curiosity. Yeah.
Yeah, I would presume so, because the CC rotational gate is symmetric with respect to the 2 qubits. So the decomposed ones should be that as well.
Okay, thanks.
Mine finished.
So we have 2 results from our online participants. Someone got 0-1 with 60% probability,
That's good.
but another person got 0-1, yeah, same thing, almost 60% probability.
So 0-1 seems to be around 60 to 70, and some got 1-1 with 99. But that, I think, happened to me this morning as well when I ran it again. But these results, which are not shown now, were from yesterday. So, I mean, what you can take away from this tutorial is the workflow for solving an optimization problem using Qiskit. So if you have any other type of optimization problem, you can start with mapping it to a QUBO form. And then from QUBO, you know how you get your cost Hamiltonian. And with your cost Hamiltonian, you just plug it into QAOA and use a classical optimizer to optimize your parameters of the circuit.
How do we understand this confidently incorrect result?
It seems like one of the qubits have a very high, but it shouldn't be, if it was like bit flip error, it should be like 50-50, 0 and 1, because it flips from 0 to 1 and then it flips back. So I don't know. Why is my job taking so long time? Can I interrupt the kernel? Job status. Job is actively running. Okay, then it maybe be done soon. But at least some of you got it to work.
Interesting. Any questions? Maybe that means we're ready for another coffee break. Final chance, questions or comments?
I really appreciate this. This is really great. So thanks for putting this notebook together. It's really makes it easy to get, as you say, your hands dirty with these problems. And I think that's fantastic. So thanks a lot. Hope everyone had a chance to do the exercise.
Yeah, I would happily share the notebook with you as well. So we can use it in-house at the episode.
Fantastic.
And can we put the notebook on the lesson page for the school as well?
Yeah.
So that everyone can access it later.
Yeah, I think it should be up there.
Okay, good. Thanks. Okay, let's go for, I don't know, 15-minute coffee break, and then we get back and hear from Hannu Reetu on random quantum walk. Quantum walks. Indeed. Okay, thank you. 15-minute break.
Now it is okay. And now, okay, great. So I must say that I'm learning these quantum walk things myself, so I'm not very deep into it, but I hope it would be useful for someone who is in the same stage. And well, other thing is I'm from VTT, and we are not academics, so we typically need to work in some projects, and everything has to be done in this way. But luckily, in some project I can, at least we are planning to use these quantum walks, and that's also part of things. And actually, there are a couple of examples which are related to this future work. So some starting phase of what we would, I think we could do with these quantum walks. I mean, find some applications is the we are aiming at. So in my slides I have many tutorial things, and I noticed that in these lectures many things have been already explained, so I skip most of that, but if you like you can find them, these slides. Look at, well, except one of those slides which I look at. It's this. It's about the permutation operator, because in these discrete walks, the movement of a walker, they form a kind of permutation of basis states, and the reason is that this kind of, you can associate operator to this, which is unitary. And here I just explain why this is unitary. So this permutation is bijection from these indices from 1 to n to itself. So I denote by p, and the permutation operator is this S. So if you know this get and bra notations, for instance, this first term is an operator which projects to the first basis state and then replaces it in a way with p of 1. So it makes permutation of these coordinates. If you think about the coordinates of vector in these spaces, for instance, this first basis state is a vector where first coordinate is 1 and all others are zeros. So after this acts on this basis state, it replaces it with a vector where this 1 is moved to the position p of 1. And, in any vector, it just permutes the coordinates. So I think in terms of this walker, the walker would move from node 1 to p of 1 and take the amplitude with it. So it's kind of, well, this just so that it is unitary by taking the adjoint of this kind of is just it means that you change this, interchange these terms, and this is because you can interpret a ket as a as a column matrix with one column matrix, and bra is a one row matrix, and this is like matrix product. And when you take this, it involves the transposition, which changes the order of matrices. And then if you multiply these two operators, you get this kind of, because these are orthonormal states, then in this multiplication, say for this term only this one survives, because this is orthogonal to all others. Then you multiply and you get this kind of thing. So you get like in permuted order of this, but that doesn't matter because this is just sum of matrices and order doesn't matter. And because this is bijection, all of these basis states are here exactly once, and that's unit matrix. Okay. So let's skip several. So first, I remind you a simple random walk on a line of integers, seen as a graph where the integers that are next to each other are connected by a link. And then start from, say, 0, and you flip a coin, fair coin, and if you get one value, you say 1, you go to the right, and if you get 0, you go to the left, and you continue this process at each position. You decide whether go forward or backward, and this is you can solve this exactly. But interesting is the asymptotic behavior. So PTN is probability that you find a walker at position n, where n is one of the integers, and t is time, how many steps you have done. And for large times, the probability distribution has this kind of Gaussian envelope. So it's centered in 0 and has the standard deviation equal to square root of t time. So it spreads like this kind of law, square root law. And okay, but quantum walk on the same graph Z is defined as this in the following way. So you need some Hilbert space. Naturally, it is just some. Well, this time it is infinite because the Z is infinite, and it appears to be this L2 space, which is this infinite sequences of complex numbers with finite sum of squares of these numbers. Or you can think about it as infinite vectors with finite norm. And these are exactly these K's are those vectors. So if these basis states are like eigenstates of position of the walker. So this, if the walker is in the state get k, it means that if you measure the position, it's for 100% you find it in the node K. And then you need a coin, which in this case has two states, like the classical coin, but this time there is no randomness in. I mean, you don't flip anything this way. And by the way, that's the reason why there is this name quantum walk and not quantum random walk. So this is the correct name for this, because there is no random coin flipping. But this coin state, as in classical case, 0 means that you move in a way to the right. Yes, and 1 means you go to the left. But in this another different sense, that for the 0 coin you have this kind of shift operator, which is again a permutation in this. You just move each number to the right, and that's of course a p action. And the other one is to the left. So from I you go to the I minus 1. And this coin decides, coins, depending on the coin state, you choose S0 or S1. So, the walk itself is a repeated action of the unitary of this quantum walk. And the unitary is like this. Yes, you need also a coin flip operators, which you can take Hadamard operator, which kind of make a mixture of zeros and 1. Well, this was already there many times here, so I don't know. So you have this kind of operator acting on this L2 times C2 space, where C2 is the coin space basis. So there is first you act with the coin operator Hadamard, or the coin state, and then you project to 0. And if you have a 0, then you act with shift operators S0. And other cases, if your coin is in project to the coin state 1, you act with this unitary which goes to the left. And again, because this is can be shown easily that it's a unitary. And what happens is, of course, you must decide also the starting state where you start. Usually you put the walker in the 0 state. But there is also choice of coin state, and it appears that depending on the coin state you get different. For instance, this kind of choice ensures a symmetric walk. So if you start from, say, 0, you would get some skewed distribution. And here is the walk after 100 application of these steps, which means that here t equals 100, so you apply 100 times the unitary to the this initial state. And here the dashed contour shows the how would a classical walker do in this 100 steps, this kind of Gaussian shape, and quantum has this kind of much broader spread. Actually, the standard deviation can be shown to be linear in t. Here it was square root of t, and so that's one. So linear in t would mean it's like it's walking deterministically in the direction. So here it is around half in both directions. But of course, if you measure the state up to 100 steps, it can be anywhere. It can be here or here, because you get a superposition of position. So, well, this case is also exact.
I have a question.
Yeah.
Yeah, so I actually had a question about the shape of the graph. Now, obviously, this is a discrete version, but what this was reminding me of was trying to fit a rectangle, like trying to fit a rectangle using like a Fourier transform based on how many indices you have, and the oscillations are much wider. So is there a mathematical term for this shape?
Sure, I understand, but yes, Fourier transformation is used to solve this. This is exactly solvable. Well.
Okay. All right, then, thank you.
And also the two-dimensional can be solved. But I don't show them, they are quite cumbersome. But yes, I forgot to write here. I used this book by Portugal, Quantum Walks and Search Algorithms. Well, I kind of, if you are interested in these details, there are a description. But I just wanted to give an idea how these are defined. Okay, next I turn to graphs, finite graphs. And a graph is a set of vertices and set of edges. And edges are a set of pairs of vertices, meaning which links edges you have. And it can be described by adjacency matrix. When you have n nodes, adjacency matrix n times n, symmetric matrix in case of simple graph. And it just indicates whether there is a link between a pair of nodes or not. So for instance, in triangle, it's full graph, and there are all possible links are there, all pairs are in the edge set. So it has zeros on the diagonal because there are no self loops. But otherwise, any pair, for instance, 1, 2, is there, 1, 3 is there, and so on. So that's how graphs are described. And here are a few general notation about the quantum walks on finite graphs. So then you have a vertex set, finite, and you assign again the position states which are form an orthonormal system for measuring position of the walker. So we this get V means that if you measure Walker in this state, it will be definitely in the node V, and so on. Then we need a unitary which describes evolution of this system. You start from some vertex and then you run this, and sometimes needs a coin, but there are also coinless walks. But anyway, after T steps, you can ask what is the probability of finding Walker in V, in node V, when you measure this state. You project through this and find amplitudes and so on. And of course, it doesn't show any convergence when T time goes to infinity, and that's because of the unitarity of the evolution. It also depends on the initial state. I mean, this reason for this non-convergence is a kind of quasi-periodicity, because U is unitary. Unitary, its eigenvalues are this kind of to say powers of one, or so, and then if you expand the initial state in the basis of eigenvectors of this U, then there happens only the evolution is raising these eigenvalues into power T. And because they have this form, when you take a very large time, you can adjust all of these phases to P, or multiple of 2P, arbitrarily close to 2P. And that's why it returns to the initial state. In this book, Portugal's book, there is a proof of this. So a distribution that makes more sense is a kind of average probability distribution. You take some large time T, and probability of finding Walker in V is defined in this kind of average over all times and divided by T capital. So, and T is very large, it kind of averages all these cycles and so on, and this kind of thing usually converges, and it's noted by P of V. But it can converge very slowly because of these long cycles and so on. And again, in this book, Portugal's book, you have some examples and analysis, and it appears that the spectra of U is important here. If there is degeneracy or not, if all eigenvalues are different, then you can hope that under some conditions you get uniform distribution. Okay. One very clean case is this quantum walk or d-regular graph when the number of vertices is even. So d-regular graph means that all degrees are equal to some constant d. For instance, in triangle, all degrees are equal to 2. So it's too regular, but it's not in this class because number of vertices is 3, which is not even. And reason for this kind of good behavior is that you can color such graph, edges of such graph with only D colors. Coloring means that it is such coloring of edges that if you look at any node, then all edges adjacent to it have different colors. So there are no two red links joining to the same node. And that's why you can take a d-dimensional point and again take n-dimensional position space, and you can make a permutation using this coloring. So these coin states are same as the colors. So from 1 to D. And depending on the color, you move always towards this link, which has that color, say red. You move always, all nodes make this permutation along red links. So there are two endpoints in a red link, and they kind of transpose each other like this. This is the shift operator, and because there are no two colors, no color that ends up in the same vertex, it's permutation, and that's why it's a good operator. You can define the quantum walk in any graph basically, but it gets more messy with the coin, because you have to take care that you get this kind of permutation in the or shift operator. So here is one example of regular graph with D equals 3 and 4 nodes. So you can use three colors, 0, 1, 2, and this kind of coloring is correct. So for this 0 color, this shift operator would be like this. So here you have 0 color, and the movement is like this from 1 to 0 and from 0 to 1. And also here from 3 to 2 and from 2 to 3. And obviously this is a permutation. And similarly to all other colors, you don't get yes, all of them are like this. Then another type of quantum walk is a continuous time walk. So adjacency matrix itself is a symmetric binary matrix, and that's why it's Hermitian. And it can be treated as a kind of Hamiltonian. And this kind of operator exponent is then unitary. And in principle, you can use this. But now T is real parameters like time. Well, you get this kind of exponent if you have a Schrödinger equation and A is like Hamiltonian there. You would get this kind of evolution. and everything else is similar to discrete case, but here you don't need any coin. Yes, another version it would be using graph Laplacian, where you put, it's the same a except that on diagonals you put minus degrees. Okay. So now I'm closing to these topics which we are perhaps studying in the project, but anyway, first is the hypercube. It's well, you know what a hypercube is. There are n-dimensional hypercube has 2 to the power n nodes, and each node has like coordinates, which is a bit string of length n. So it's like can be nicely fit to n qubits, say. And if you take this kind of Hamiltonian, where you act on each qubit with x gate or sigma x, so which flips the qubit. The index I indicates which qubit it acts on, and it appears that the matrix of this operator is exactly the adjacency matrix of this hypercube. Okay, I forget to say. In hypercube, nodes have edge if their coordinates differ exactly by one binary. So there is difference only in one coordinate. And if you compute the matrix of this, you can see that you can have only difference in. So it is one only if there is only exactly one difference in coordinates, because this flips that. You always find a sigma which flips that, exactly that qubit, and you get one. Okay, that's one fact. And then you could have the quantum walk on hypercube using this Hamiltonian, which is also the adjacency matrix. And in the previous lectures we had this operator already. It was in the mixing Hamiltonian in the QAOA, and it has known the gates and everything. And this was pretty much the same. So I just wanted to say that quantum walk is involved in QAOA in the standard form, but it's just like saying that this is, yes, also quantum walk. But then there seems to be some new ideas about so-called quantum assisted QAOA, and I thought maybe this could be interesting. And if I understood correctly, the use case would be like in users QAOA, all these bit strings are some kind of solutions. You have made it in such a way that there is a cost function for each bit string, but it's not always the case. For instance, you could have, they actually pointed out this problem of finding minimal vertex cover of graph. So vertex cover is a subset of vertices such that any edge has an endpoint in this cover. So if it's colored, if you color the nodes in cover, then any edge has at least one endpoint, colored endpoint. And the problem is to find minimal cover set. And obviously not every, well, you can again have these qubits that indicate whether one indicates that you take a node into cover and zero that you don't. But no, not any subset of nodes is a cover. That's why not any bit string is a solution, possible solution that you should consider and compute the cost. And what they suggest is that you take this, if you can efficiently define this solution space, you can take some quantum walk instead of this quantum walk on hypercube. You take a quantum walk on this solution space. And there is a class of optimization problems that allow this efficient recognition of whether this is whether node is in the solution space or not, and this is assumed. Well, here is one example, finding vertex cover of a triangle, and then the hypercube is a cube where each vertex is like, it indicates some indicates which nodes are taken in this subset of nodes. So say 0, 0, 0 means 3 zeros means that no, it is empty. And 1, 1, 1 means that you take all nodes and so on. But you can easily see that only these red nodes are possible covers. As I said, if you take, say, only one node, this one in the cover, then what happens is this edge doesn't have a colored node in one of them, so it is not a cover. But these four ones are, so you take all nodes and these two, and all edges have one endpoint which is colored. So this is the search space. Well, I made out of this little example, and here you have some freedom of choosing the graph in the solution space. And they suggest to use so-called circulant graphs a bit later. Well, it means that the adjacency matrix is circulant. For instance, K full graph is such, and in this example I use this full graph. So So basically the problem is now four-dimensional, and I just left those other nodes out. And the adjacency matrix of this K4 is this kind of zeros on diagonal ones everywhere. And the cost, well, I decided that the fourth node is this suboptimal solution where you take all nodes. It is not minimal because there are other covers which have only 2 nodes. So now I'm trying to find the maximum of the cost function or cost operator, expectation of the cost operator, and it's diagonal as always, and I just put cost 2 to the optimal solutions and 1 to suboptimal, and start a walk in this state, superposition of all nodes, and use this QAO scheme. So in QAO you try to find optimum of this kind of expectation, and obviously we know that this would be the one solution where you put 0 amplitude to the suboptimal solution. I just tried out this, and you can compute how these operators act on this initial. So the P equals 1 in terms of QAOA. And you can compute, I used Mathematica, it gives an exact answer, but actually you can do it by hands as well, because we know the eigenvalues and eigenvectors of this A4, and also this exponent, because it's just the eigenvectors are the same, but the eigenvalues are here in the exponent. So in a way you can exactly compute what is the result of one step. And there are 2 parameters, t and tau. And it happens that all these 3 states have the same amplitude, and the third has this kind of amplitude. And if you can turn this C prime to 0, then you find the optimal solution with probability 1, because then these are equal and the whole mass is there. First I solved it numerically, and of course it depends on the accuracy. But as I said, you can analytically compute these. So this is like analytical result, and you can figure out whether you can find exactly whether there is a 0 in this. Both real and imaginary part are exactly 0. So how much time I have?
Like to have?
Maybe 20 minutes or something.
20.
Yes.
Yeah.
I'm not sure, but well, so this is a little bit, I don't know. I just I think that here you can prove that you can really find the solution in one step. So you basically find parameters, well, I denoted by x and y, these these parameters in the QA, that doesn't matter. They are just some real numbers that you can adjust. And this C prime equals 0 means that both real part and imaginary part are 0 in the same point. And the question is whether there is exactly this kind of. So these are like, if you take, for instance, if 2 equal to 0, you get some function y is a function of x. And it's here this kind of like this closed curve. So this is like intersection of this function with the 0, with the plane which takes value 0. So this would be the real part is 0 in this on this line, and imaginary the same for the imaginary is kind of, which is exactly a line, because if you substitute x equals minus y here, you get 0 for all x and y. And since this line goes through this area, it must intersect with this. There are these points where both are zeros. Well, you need to do this analytically, but you can do it with. But anyway, that's a curiosity of this example. Okay, now the circulant matrices are like this. When you have a first column, then the next is like how do you call it? You just move them as on a circle. So you move 0 one step downward and so on, and then the last you put you make a kind of cycle and move one step, and next column is similar, but then you move this cycle one step and so on. And for such matrices, there is formula for both eigenvalues and eigenvectors, which are written in terms of omega, which is this kind of root of 1 in complex domain. And actually, all eigenvalues of any such matrix is this kind of. It doesn't depend on the elements, but eigenvalues depend in this way. As I said, in this paper it was suggested that you take graph in the solution space, which is this kind of matrix. The adjacency matrix is circulant. And the reason is that then you know eigenvalues, eigenvectors and eigenvalues. And that's why we can explicitly write everything. And also you have a connection to quantum Fourier transformation, because these eigenvalues were exactly of this form. Well, this thing was there. Yes. In adjacency matrix, all these matrix elements are zeros or ones, and I guess that's why you get those. Well, anyway, this is definition of Fourier transformation of computational base element, and it appears to be exactly the yes, there is no eigenvalues here. Exactly these eigenvectors of the circulant matrix, which didn't depend on the matrix you are using. So, and you can write this operator in this form. And that's why you can write this quantum walk on such graphs using the quantum Fourier transformation. Well, I don't. Well, you can prove that actually this is true easily, and here this exponent is just diagonal matrix where you have on diagonal these eigenvalues of this kind of exponents, where lambdas are eigenvalues of A, which are for which you have a formula for any case of matrix. So it is known, and at least in general terms, you can have a efficient, at least in some way, practically probably not in terms of gates, because you have only Fourier transformations and diagonal matrices to implement and their product. So at least you can formulate everything in like quantum gates. Another type of quantum walk is staggered quantum walk, which I was also tried to use somewhere, but it's a discrete walk on graph, and first you select divide nodes of the graph in such a way that in each set, induced subgraph of each set is a full complete graph, so all nodes are connected within those subgraphs. And also it's always possible, because isolated node is also considered a complete graph. Then you take several of such tessellations, they're called, in such a way that any edge can be found at least in one of those tessellations. So they kind of cover the graph. Well, then you make this kind of, for each tessellation and each complete graph that constitutes this, in a way that for those nodes which belong to that subgraph, you make this kind of equal superposition, and then make this kind of Hamiltonian, which is like Grover operator for those, made out of those vectors. So it's kind of like mixing those vertices within each and between those complete graphs. And this is a Hermitian operator, and you can make for each member of this tessellation cover, you make these matrices, operators, and then make unitaries multiplied by some constant, some real parameters. And this is unitary with those parameters. And then you start from somewhere and just apply this unitary many times. Yeah. And I just thought maybe you could use this also in the quantum walk assisted QAOA and try to use it as a quantum walk in the solution space, and simply take all these parameters equal to each other and use it as this mixing operator. So here is one example of this tessellation. So take full graph with 4 nodes. So this could be one tessellation. You take this triangle and this node. So the triangle is complete graph, and this is also considered one. But this doesn't cover all edges, so these are outside, and that's why you need more. For instance, these 2 others, this triangle and this node, and then this triangle and that node. This already covers. So I used this and I made this operator, and again in the similar way used it in QAOA type. And I just ran it on Mathematica, and so this is like amplitude of this. Well, this was exactly the same problem of finding a minimum vertex cover in triangle. So you can see that this is the amplitude of the non-optimal solution. So at least you can see that you can, by changing these 2 parameters, you can make it oscillate heavily, and at some points it's very close to 0 and so on. Also with 1 step. Okay. Okay, but I'm almost in the. So the last example is also this kind of new beginning of. I have been working on this kind of non-backtracking walk-related issues, and I wonder whether there is a quantum version of this. Maybe it could be used for something. So non-backtracking walk is this kind of extension of classical. So if a walker takes this blue step, then the next step can be only this yellow, so it cannot immediately come back. So it appears that it's quite has interesting applications, and So how it can be described by this kind of directed graph. So each link is doubled, both direction are taken into account. And then you can create a matrix where each row and column are these edges, directed edges, and you write here 1 if the corresponding step is possible. So this is the non-backtracking matrix, but it's not symmetric, and that's why it defines a directed graph, and it's bigger than the original. Well, for this graph, this non-backtracking graph looks like this, and well, a simple idea is just to use coordinate non-backtrack is to use the quantum walk on a directed graph, because that's what you have here, and it was already depicted here, and the idea is that well, it's not possible to do in any graph, but if there is certain condition that all edges are in some directed cycles, then you can choose a set of cycles in such a way that they cover all edges in the graph, and then you have a coin which decides which cycle set you use. So, well, not just cycles, but set of cycles which cover all vertices. You can take one long cycle, and then you can take self loops also. So you can, and the coin decides which cycle you use, and you get this kind of movement. Okay, for instance, for this graph, you could have this triangle like cycles. For instance, for this green cycle, you take this cycle and self loops on all other, and this defines a permutation in the position, and that's why it. And then you have gates for this, because any cycle can be. So cycle is this kind of permutation where you first element is mapped to the last, and this kind of, and it can be decomposed into the so-called transpositions, which are one when you swap two elements, and you need for n cycle you need n-1 such swaps, and these swaps are simply the same as quantum swaps, and but eventually you need to also this coin state which selects the cycle set, and so it is like a controlled swap gate, Fredkin gate. For instance, here is one 3 cycle could be, if it's controlled by this kind of coin state, it would look like this. Well, at least there are some cycles, and well, I guess I don't have time, but for this triangle, I solved this quantum walk analytically way. But classical non-backtracking walk would be like this. If you choose this edge as a first step, then you can only go clockwise, otherwise there are only two. But in quantum case, I mean, this non-backtracking graph would be two isolated triangles. Well, there should be arrows here also, but anyway, this is quite simple. But you can make these unitaries and on each cycle use Fourier transformation to find again state of the cycle movement, and then you should diagonalize the the coin state corresponding to certain cycle. Well, I think this is quite in Portugal's books there are several examples of similar things, that how you solve exactly the quantum. You need to diagonalize the unitary, then you know exactly the evolution of any quantum state. You just expand the initial state in the basis of that unitary, and then each of these components, they evolve. Phase factors raised to some powers, and this could be done here also. Here are the 18 eigenvalues of that unitary. So all of them are distinct. So I guess you can conclude that this limiting distribution would be uniform. So personally, I think this is difficult to extend to other cases when these cycles overlap. But I'm now thinking how to diagonalize. This is impossible in a more general case, and definitely try to look at other graphs, and you can simulate at least them, and try to think how these unitary matrices could be useful in something. Idea right now. Yeah, and I estimated some resources needed in quantum computer. Of course, these Fredkin gates are not terribly costly, but are somehow costly. So you get some rather long, deep circuits. But anyway, this is like ongoing works. So please, if there are questions.
Thank you very much.
All right, so we have a nice 2-hour session with me and Karim on the theme. I think an underlying theme is quantum chemistry and material science. My talk will both start by zooming out a bit on this subject. Some ideas that I haven't published yet that may be useful to you, might not be useful to everyone. And then I'm going to use that as a transition for Karim, who will be talking more about a specific material science application of quantum computing. I work at RISE, both in, I have different roles at RISE depending on the projects that I'm working with. Either I lead them, I coordinate them, or I research inside of them. And when I'm a researcher, when I have that hat on, I'm working on quantum computing, which is my main research area of interest. I have a natural science background from Uppsala University, where I once studied at theoretical chemistry at Ångström. And it's nice talking to guys here yesterday. It's kind of a small community, and you get kind of blind for how small it is. I found many of you being connected to professors that have been teaching me, that have been colleagues of me, and that have similar interests. So that's always delightful. So one of the things that we're working with at RISE in collaboration with the NCCS, it's the NCCS funded, is this idea of distributed computing. So what do I mean by that? Every computation you can make with a digital system is distributed in some aspect. But what I mean is, so on the European level, there is all these terms thrown around that are kind of gathered in some kind of quantum, in a compute continuum, where HPC is one part, but more and more I see calls mentioning these under the umbrella term of it being a continuum. And somewhere in that continuum exists also quantum computers. And it depends on your perspective on quantum computing, if it is a separate compute environment that should be treated as such, or whether or not it is like an accelerated backend that exists in a HPC facility. But I'm going to start from that umbrella term, and then we're going to focus down on what I wanted to share. So this idea of a compute continuum is kind of new, actually, but it's gathered kind of a lot of action. I see this mentioned on a high level everywhere, where it is like a catching on trend. And as a researcher, you have to understand what people that may or may not be informed of the research mean when they say these terms, because if we don't understand them, we can't really successfully write applications very well. I think Europe is wrestling with the idea of understanding what this means. But in general, I think the underlying challenges for all of these compute infrastructures are very much the same, regardless of what accelerator backend you're using, right? There is a user experience, which is very much tied to like a complex logging process. You need some kind of SSH access, maybe. You need to maybe set up tunnels to access your work machine. If you're running on HPC, you have to like master understanding how Slurm works or any kind of scheduling environment like that. There's also the problem of understanding if your job will run and when it will die. I think, what is common for many of the HPC facilities is this focus on result rather than reliance. There's data management problems that you have to solve to understand how to store the data that you're producing, and this data transferring can be very time-consuming and costly. So I think there are several integration issues. Really, as a researcher, I may not be interested actually in myself hand selecting backends for my calculation. Ideally, I want to formulate a problem that the system then takes care of finding the optimal backend for me to use, depending on what problem I'm trying to solve. But with a lot of this HPC and also the coming quantum computing infrastructure in Europe, I think we might see the same problem, that there's very little APIs to work with. There's really no or little support for automation tools like GitOps and continuous integration and delivery. Problems with multi-factor authentication, and also there might not even be internet access to compute nodes. Yes, so let's see. I have lots of stuff to go through, so I'm handpicking a bit to see that we can make it on time. How is the schedule? We're running for 1 hour now, so like 10 past. Is this the shift of the schedule? 10 minutes? Okay, I see. So the workflow as for a researcher is very much like it involves manual interaction, in that you need to set up your simulations or experiments. You kind of value outcome over efficiency many times. You want to quickly obtain accurate and valuable research results, essentially. They are exploratory in the sense that they can be less predictable and require more hands-on adjustments, as you might not know whether or not you need to adjust parameters in your calculation. And also they might require manual scripting for batch processing and queue management. And then the question is, why shouldn't we be using cloud for our calculations? And these are also very complex and cumbersome for researchers to operate on. And also, I think many of these popular Kubernetes, etc., they're not really designed for the kinds of workloads that you might want to run on HPC or even a quantum computer. And I'm using I'm taking the generalist approach here of talking about how like a researcher interoperates with many of these complex compute resources. And there is also like the larger context of vendor locking in and dependency on network access. When we centralize these kinds of resources, there are kind of sovereignty problems that come with them, you know, because we're making the resources vulnerable. We'll not dwell on that too much. So I think like there is like a scale of access where HPC offers, like it's ideal for scientific and large scale simulations. And then you have your local computer that you want to use for like development and testing. And then cloud is more aligned with like data storage, big data processing. And somehow all of these things should ideally interoperate and offer like a cohesive way of working with data. And as a researcher, I find this especially lately. We have so many backends and we have so many technologies, and there's kind of like there are fewer tools that really make use of and offer a way for me as a researcher to make use of all of these things without having to write something very highly specialized. So I'm looking at the screen because the Zoom is covering my laptop screen, with a bunch of info. So maybe we could think of a service that could combine all the strengths from all of these different compute sources. So we could simplify cloud access for HPC users and seamlessly migrate to cloud after using EuroHPC, for instance, and create cloud APIs that we can access, so we can access HPC results. And we also kind of want this local property of being able to like linking and sharing and using local resources. And somewhere in this lower left corner also exists the quantum computer as a part of the HPC facility. But like this is to do this yourself, you're kind of looking at a very complex software stack, and what you want instead, like having one really complex piece of software that has special interactions with all of these different stacks. The idea that we're working with is having this unified API towards this compute continuum. Hello. So on the user side, the software becomes less complex because you're dealing with a unified API that can communicate with all of these different backends. So Colony OS, which is this software framework that we're developing, is built on this idea of a meta operating system, and essentially it's an operating system within the operating system of your computer that allows you to connect middlewares essentially towards these different compute stacks. So you have executors that can take on different workloads and perform them on different backends, regardless of what they are really, whether or not it's an little IoT device, whether or not it is a quantum computer or a supercomputer or a public cloud. As long as you have a definition for this executor and what kind of work it can perform, there is no problem with coupling it to this meta operating system. And you can also switch these out. So Colony OS is kind of a large and mature code base at this point, at least from a research standpoint. It's written in Golang, and there is a little QR code that you can use to get access to this. It's open source, and it's focused on this idea of decentralized computing that uses all of these different resources. And it actually has a pretty nice proven track record. The core parts of Colony OS have been used. Maybe I'll show some slides on this, but it's been used by a company called Rock Sigma, and they're using it to evaluate seismograms in large mines. So this is when you dig into the use case, you kind of see how it maps to other things as well. Maybe I'll dive into it, but it's just an example of how this kind of system has been deployed successfully. So a colony, the concept of a colony in ColonyOS is like a distributed cloud consisting of loosely connected executors, forming a unified compute unit. And these executors could be implemented for any kind of backend, as I said, and operate behind routers and whatnot. So I can have, when I do my development on my local machine, I could deploy it on an executor, running on Leonardo, or in our data center in ICE, for instance, or it could be on a quantum computer. Let's see. So let's just quickly run through what the guts of this whole thing, conceptually at least. Around this meta operating system is an API that exposes resources. There is a broker that handles communication towards cloud and Kubernetes, and through this, through this API we can define, we can provide definitions for a node. Colonies. Oh, okay. Someone spoke something. All right. So an executor can be registered to a colony server, and I have one running on my laptop, for instance. And that then connects via the internet to an executor on an HPC system, or it could be an executor on a cloud, or on an edge compute node. The user then creates a function specification. If you look at the top, and it contains conditions, a function name that we want to execute, and some keyword arguments. And the executor then registers to a colony system, and the user or executor submits this function specification to the system. And then the executor is assigned a meta process. So this could be assigned to different executors, and the executor interprets the function specification. It syncs data from this meta file system and executes the function. And this file system is accessible via, it's a way of essentially syncing local storage between these executors. And then the colony server monitors the execution, and it stores the history in a database. So you can conveniently look at all executors that are actual and what kind of work they perform. And what's interesting is that it kind of creates this separation of concerns, where I might be, as a researcher, only interested in really developing an application, like writing a Python script that does some interesting analysis, maybe runs a Qiskit simulation, what have you. And they, as a user currently, the problem is that you have to have very deep understanding of the platforms that run your calculations in order to do them. But this kind of abstracts away. It doesn't, not without the ability to get insight, but it abstracts away some of the need for understanding the platform, and instead the user can actually focus on describing these function calls. So I think that's a strength, because what I develop on my laptop and I can prove works on my executors could also then be just ported to an executor that has different resources, or maybe is more powerful. So executors, again, they are kind of microservices designed to execute specific functions and integrate with other platforms. So the executor is kind of the unit of system integration, and it can reside anywhere, literally anywhere on the internet. It could be inside of a notebook or what have you. And this brokering system is a loosely coupled system. It uses takes some inspiration from blockchain ledgers, in that it stores the compute history in a ledger that is available to all of these executors. I'm not going to go deeply into that. And it allows also dynamic allocations of resources and the optimization of performance, scalability, and so on. And also energy. This is something that I know my colleagues are working on, quantifying the energy requirements and demands of these executors, so that we can use that as an optimization parameter for how we allocate work across executors, essentially. I hope this makes sense. As someone who's worked and thought a lot about systems, this makes sense to me, but maybe it doesn't make sense to everyone. At any rate, this is an example of a company that works with ColonyOS and has had it deployed for a long time. So Rock Sigma, they work with seismic processing of underground mines. and it's used by Elko AB to analyze seismicity and process massive amounts of data from one of the largest open mines in the world, or underground mines, sorry, in Kiruna and Malmberget. So this is run on Preem. I see this is not on the gas station Preem. Let's skip some of this to get into the interesting stuff. Yeah, okay. So the execution history, as I said, can be stored as and viewed as a ledger. So it allows the whole system to keep track of the execution throughout the history, which I think is powerful. It also provides a very rich logging system that you can utilize in order to trace the processing. I think this is also for anyone who has spent any time working with these kinds of orchestration systems like Kubernetes or what have you. Digging out logs is oftentimes troublesome, and understanding why things fail is really important. And I think this is one of the things that we have tried to solve in ColonyOS, which is relevant for all kinds of computational work. It has a very rich command line interface where you can query your server to see all of the different information you can get from and about different processes running in your system. So we can see, for instance, this is a processor that will get assigned if there is a container executor that has this edge property. And you can also set conditions on what kinds of resources are required for this process to be executed. And mind you, this could be, now we're just looking at classical computation, but it could, and I envision this to be useful for quantum computation as well. If we have multiple different compute backends for quantum computers, we could just as well define this in terms of what resources we want to have access to. Exactly. So these can be completely cross-platform. This is a process graph that highlights how a workflow might look like, and the interdependence. So you can schedule jobs that depend on each other. And if you're thinking about like a large Qiskit script in Python that just runs through from top to bottom, my approach is instead to like break apart this script and to see if we can formulate a workflow where each part of the script can be ran on the most suited compute backend. It's very easy to set up this environment. Here is a QR code that you can scan that puts you right in the direction of the repo. And setting up a development environment is really easy if you have like a local container executor environment. This gives you examples of how you can use Docker Compose. So that is what I've done. I've set up ColonyOS on my local computer. And what I wanted to discuss, this is some ideas that I have for how this could be useful for quantum computation as well, is that as a researcher, when I explore different options in terms of how I can model a certain system, I might be interested in exploring a number of different parameters for my calculations. So for instance, I might want to define a grid of optimization parameters over which I run my calculations. So I might want to choose, if I do a VQE calculation, I might want to use different types of optimizers and explore different type of tolerances, optimizer steps, and so on, in order to obtain an acceptable output, which could be, an energy calculation for some system if you're a quantum chemist. And it would be interesting also to collect metrics of what it would mean to run calculations on different European or compute backends. So this is a kind of a large system that I'm looking at, even if it's just a toy example. So you could see this as a nested workflow. I'm just going to show what this means, both in terms of like pseudocode, but also in terms of the workflow. So for each ansatz, I might want to use different optimizers, and for each optimizer, I want to maybe use different hyperparameters. And then I might want to use different noise models on each set of hyperparameters and optimizers to, in the end, see which of these setups are more or less prone to being affected by noise. They all are, but it would be interesting to see if we can create kind of a profile of how this noise distributes over different ansatz and different formulations of the VQE. So you could imagine something like this, where you have you generate your you assemble your Hamiltonian from integral calculations, and then you prepare the ansatz. This is just one ansatz example. Maybe this is not too readable from the audience. I'm not sure. Anyway, I'll get into this later. Then you could set up different VQE approaches for which you then run a series of noise simulations.
So Erik,
Yes.
there's a question here from the chat.
Okay.
What is the fundamental difference between this Colony OS and current Slurm job management, besides it being through the internet?
Okay, sure. So the thing is, what I want when I submit a job to an HPC facility, I don't really want to interact with Slurm, really. I want an environment where I can develop my calculations locally and then throw them into a system that has an executor definition that allows me to just take that locally developed code and then port it to a facility like Leonardo, for instance. And if you use Colony OS as an abstraction on top of Slurm, you can achieve that. And I think that's interesting and powerful because it removes some of the work of just trying to understand and interact with Slurm. Instead, you can rely on a system where you have developers that have created an executor that interacts with Slurm for you. I'm not sure if that answers the question, but think of it as a layer of abstraction that removes some of the complexity of interacting with many of these things. And Slurm can be a beast. I've tried to set it up on a few machines, only successfully a few times. So it really is a beast to work with. Anything else? No? Okay. Cool. All right. It's important to note that each of these pieces along this workflow really could be ran on any compute backend. For instance, I might want to calculate for a quantum chemistry problem, I might want to calculate the 1 and 2 electron integrals on an HPC machine that has like CUDA acceleration. And for those of you who are not, I'm not sure how well versed people are in quantum chemistry, but what I'm talking about is essentially the interactions between the energy contributions you get from just one electron and versus and I realize now that this was a terrible way of introducing this concept, but also the integral calculations required to account for 2 electrons interacting. And if you, if you have done any kind of DFT work, the 2 electron integrals are the things that you kind of approximate using a density instead. At any rate, I'm putting them there, and so my point was not to dive too deeply into this, but rather to say that you can pick apart the whole program and not dedicate like an entire machine to running the whole thing. Really, and I think this is we want to use the quantum computer in the end only for the things where we know we have. We get something out of it, right? Because they are costly both in terms of energy and, well, actually they are just costly to access. So ideally, when we finally port something to a quantum computer, we want to know something about how noise affects the outcome. So my idea was to use Colony OS for this. This was my solution, suggested solution. This is a blog post that I've written and that I'm just showing you a bit of. I'm going to get to some results in the end because I've already spoken a bit about Colony OS. But as I said, it's a distributed microservice architecture that allows us to do workflow orchestration. And also, most importantly, it supports fault tolerance under scalability. And I think this is a key thing. It's like a key selling point of Colony OS. If I submit a process and I have an executor running, I know that my process will get executed eventually. And if I pull the plug on my laptop, the Colony OS server will still have the definition for the process and know which executors are connected. So even if I have an executor on my laptop, another executor can take over the work. And And that's why, like, when we deployed this system for LKAB, it's been running for a really long time with very little intervention, because it's designed to fail. It's designed to handle failure, I should say. Designed to fail, that's something else. It's platform agnostic in that the executors can be defined for any kind of backend, really. So I wanted to, my naive idea that I wanted to test is like, can we find a way of finding the most optimal problem formulation that we are the most interested in porting to a quantum piece of quantum hardware based on some initial ansatz and some initial system that we want to explore. And there are a number of different metrics we can utilize to actually quantify how our calculations are affected by noise. I'm going to mention a few and also talk a little bit just briefly about noise modeling in Qiskit, just to, and this is probably a repetition for a lot of you. So I'll brush over it, and maybe we can view the details if you have questions. There are a number of ways we can model different kinds of noise in Qiskit. I've employed using this depolarizing noise model, for instance, where we're kind of creating a representation of where the quantum state loses its coherence and becomes a completely mixed state with some certain probability P. So mathematically, for a single qubit state rho, the depolarizing channel that is used is defined as eta of rho is 1 minus this probability times rho plus the probability, half of the probability. So it kind of generalizes for a multi-qubit system. It generalizes to a depolarizing channel. The depolarizing channel generalizes by applying this noise to each qubit collectively or to the entire system, depending on how the model is implemented. I've also used this bit flip noise model for these examples, and I want you to keep in mind, I'm doing these calculations not because essentially the system is interesting. I've just run like a ground state calculation of water, and I'm using a few noise models. So it's more interested from a systems perspective than it is from a perspective of the details of the calculations. Because first I needed the system in place before I could do anything interesting. And that last interesting part is probably what will end up being potentially publishable. Bitflip represents the error where qubits with some probability flip from a state 0 to 1, and vice versa, similar to a classical bitflip. And I've also implemented some ways of measuring the impact of this noise. Shannon entropy is one measure that could be used, and it measures kind of the randomness or the uncertainty in the probability distribution. For a discrete random variable with possible outcomes, you have the Shannon entropy defined as such, as h of x. And so it's a bit it's not maybe so meaningful to talk about this as one value. You really need to look at the distribution to understand entropy. But maybe in general we can say something about that. Low entropy, we have a distribution that is concentrated on specific outcomes, and high entropy means a more uniform distribution of noise. There's also divergence metrics we can use to calculate, to look at how noise impacts the calculations. So to probability distributions, you have this expression for the divergence of P and Q, which relies on the Kullback-Leibler divergence from P to M, this average distribution, but it is symmetric, and it allows for most importantly, it can handle cases where the probability is 0 essentially. So in general, we can say something like that for higher divergence values, we have a greater divergence between the distributions due to noise. So this could be a way of indicating that a certain calculation might have larger impact of noise when we deploy it on a real backend. Exactly. Okay. I'm scrolling back down. So I have. This is something I've designed for myself. I'm going to show you a bit here. So what I've done is that I've written I've implemented an executor and built a workflow for doing exactly the workflow that I showed you above. A simple calculation of the ground state of water using Qiskit with various VQE setups. And then all of the data from this calculation is dumped into an SQLite database. And then in front of that, I have a little API that exposes this data so that I can search in it. And then I've developed two front ends that just allow me to like inspect the data. So essentially, I've got a metrics table where I can rank the calculations based on different properties. I'll show you this demo of this. And also, I think more importantly is like this idea of a workflow graph. So these are all of the nodes and the key pieces of this calculation. And I think maybe if I just show this, I'll show this live from my front end instead. So this is the full calculation in terms of nodes in the workflow. We start by running these two integral calculations that are then combined into a Hamiltonian. And from that Hamiltonian, we formulate two different ansatz calculations. And from those, we can spin off a number of VQE simulations and in the end, apply different noise models to them. And this is just one system. And you can easily see how this could expand if you were to look at many other different kinds of ansatz and hyperparameter spaces. I think graphs are interesting in general. I spend a lot of time on graph analytics where it gives something, where it adds something of value. Graphs are naturally structured to also be implemented in for graph neural nets and machine learning. And one possible implication of this could be that if I have the definition of a problem in front of me, it's not unfeasible to imagine that you could train a model that could give you a first estimate on what the problems might be for a given backend based on your problem definition. That's obviously stuff that is long down the pipe, but if I compute the ranking across all of these calculations, the noise simulations that is, we can rank this basically on optimal value and JS divergence, and that gives us this output of where this, for instance, is a particular setup that generates within our data set the calculations that has the lowest susceptibility to noise and the best agreement with respect to the ground state energy in our trees. And I realize these numbers are okay, so they were not rounded in this front end. I'm sorry about that. It's like work in progress. But I also exposed them via this metrics table, and now Zoom is giving me a very helpful menu that is blocking all of my access. Let's see. Okay. Yep. Okay. So here is the same, essentially the same data, but in a table format. Right now, these UUIDs are not very useful, but they allow me to identify which calculation yielded the most promising results. So the ambition here was to show like how we can use this state-of-the-art orchestrated for distributed computing. And the particular use case here is quantum computation. I think there is something here. I think there is something that could be developed further where we might be able to use a system like this. Maybe it is called OS, maybe it's something else, that allow us to run these kinds of workflows, but utilizing different backends. So again, I'm interested in exploring how this could be applied to many of the different backends for quantum computers that we currently have available. Because now, when I know which calculations are the most promising, I could build a system that gives me trial calculations for different backends. And also it has this further like graph analytics application, which I think is kind of cool. Yeah, so all of this has been developed using funding from ENCCS. So this is, while I have to clean up the repo a little bit and distribute it so that you guys can access it after this event. I'll have to get back to you on that, and also remove my. I have to reinitialize my Git repo. There are some confusing late night commits that have messages that are not very helpful. But that's all I wanted to present for this session. Okay. All right. So I will take questions.
Thank you, Eric. Yes.
Please.
Thank you for the great presentation. Maybe I missed it. I was just wondering, since there are multiple systems that have their own security things, logins and all, how are you able to handle that? Like, is it collectively?
I'm sorry, my friend, but I think the answer, it depends. It depends on the particular system. But we have successfully implemented executors for the Leonardo HPC system, for instance. So we have had Leonardo executors. So, I mean, if we can handle that, I'm sure we can find ways of handling authentication to other services as well.
I mean, like, does Colony always require that the executor handles the authorization and auth?
Right. So, yeah, okay. So, like, do we need to build executors that also are able, like, have the rights to handle authentication? I think I have to get back to you on that. It's interesting to discuss, but it's hard to do without, like, dealing with the details, I think. But it's a good question. Like, this is, of course, it has to be solved. It has to be solved in some way for this to work at all.
Yeah, it would be interesting because we had that same problem when we're trying to connect Cal9, the quantum computer at Jamesh with Lumi, and we were just running into problems. How do we have uniform authentication across the two?
Yeah. I think Colony OS is not trying to solve the problem of uniform authentication. I think what you're looking at is executors that are capable of handling specific authentication platforms for different systems, at least currently. Yeah, that would be my answer to that question. Anyone else?
What more questions do we have?
Please.
It's a really nice presentation, actually.
Cool, thanks.
And, actually, it's like when you make abstractions, actually. So you want to make HPC on one side, and the quantum on the other side. And you want to make the abstraction for the chemistry, like this kind of a community, right? If I understand.
Right. Okay. So yes, we are creating abstractions. I mean, in this particular case, I showed how you can use simulators like Qiskit and evaluate a number of different calculations that you can then port. Like you can select a candidate calculation that provides you with the optimal setup that could then be ran successfully on a quantum backend. So like it is a tool for a quantum chemist, right? Because of course, everyone can write their own Python script that does this and spits out a little SQLite database and what have you. But this comes with the added properties of being adaptable to multiple different backends, right? It's like platform agnostic, and like that takes time to write in a Python script.
But I have one specific question about the resources. Like, basically, as of now, it's like, for suppose, if a user just submits his job using this platform, and you have a budget basically for each platform. If you are using a Lumi or some like HPC cluster, you always restricted to this budget.
Yes.
And it's like how you're taking into account.
Yeah, I think like realistically, you can't really bypass that. If you have a system that is set up with Slurm, like that sets the limits for what you can do within a certain project. So I think the executors have to be defined in that context. There is no alternative, I think. But it does abstract away like the specifics of having to write these horrible SBatch scripts that are very error prone and very verbose for Slurm, and it gives you a format that is much more manageable. At least like us as a researcher starting out, it was kind of hard to understand all the different properties of SBatch and interacting with Slurm. That was like a thing you needed to learn. So here the executors provide some abstraction within Slurm, but it cannot bypass the queuing system, obviously. Like this is something we can.
Yeah, because actually Maurice, he's involved in this COE race project where we have this LAMAC API. Where we are also trying to solve the similar problems.
Okay.
What users from different community are having, like there is a community in the CFD who want to use the EuroHPC JU systems or all these kind of systems, and they want to use the API, like a Python, like a PyTorch or TensorFlow. It's like everyone has the same kind of a problem sets.
I think so.
Yeah. And then it's like we try to resolve the identity management by hosting on the GitHub or some like so it's abstraction at some point is becoming very difficult in terms of
yes yeah, no, sure. Yeah, there are pieces of these systems that we always have to respect, right? Good question, thank you.
Very interesting. How far can this go on, this abstracting away of the underlying sort of machine level? Is it likely that we'll ever get to a point where you don't have to model your problem to an HPC system or to a quantum system? The machine is taking care of that and sort of translating your intent?
Yes, okay. So how far can we get in the abstraction? The idea is that, yeah, if the idea is that you, as a researcher, you could work with like an expert in an expert developer that works with NordIQuEst that can help you set up an executor that has the right resources, that has the right access to the right libraries and so on. And then as a researcher, you can focus only on writing, like you can take your code, write a function specification for it, and then submit it to the system. So it's hard to provide a specific answer for how much you can abstract in the executor environment. There are different kinds of executors that can write. It could be like a Docker executor where you essentially just write like a YAML file that you can submit, of course, and then that spins up like a container executor in Kubernetes or whatever environment you have. Or you could write it in Python, as I have done. So it's got some this is mostly like systems properties, but it's got a very nice Python API. But the API could be implemented in other languages as well. This is just one good way of working with them. So you would define what kinds of functions this executor can handle. And these are all, if we look at functions down here, these are all essentially nodes in the workflow graph that I showed. Which could be, like they could be, I could just as well execute these functions like step by step and then myself assemble the whole thing. Or I could have this workflow handle that for me. So it's got some nice properties. I'm not sure if I'm answering your question. It was kind of general, so I'm.
A quantum system or an HPC system, or is the machine going to take care of that?
Yeah. So that's better limits. I think there are problems that for an HPC, there are problems that could just be like, if I don't have strong requirements in terms of how long it should take, I could submit it to a set of executors that are distributed over classical computers. It could be a HPC system or a laptop, what have you, where that means less, and it could literally just be a Python script. Run my code, give me the data. But I think we're not on that level for quantum computing, of course. Like here, you have to be really particular about what kind of machine you run. So it's different. But I mean, also, the one reason why I'm doing this is because on the European level, there is this vision of where quantum computing is an accelerator, much like FPGAs or GPUs or what have you. But I'm not seeing the systems that make that possible, because we have many different ways of building systems that can process quantum information. So I think that has to be in place before we can say how much we can abstract away with a solution like this. Okay.
Yeah, short question. Thank you very much, by the way. And I think NordIQuEst goes in the right direction, making it simpler for users. Closer. Okay. Yeah. So we have large language model scientists now with our HPC systems, and they're particularly complaining all the time. Right. It's too complex. And there's my question. When I think about virtual environments are right now solving a lot of these issues, which are in a way a gray zone. You would say, in one respect, it would be from the computer scientists to prepare the virtual environment, but then you don't know the tokenizers of the large language models, NLP libraries, and you can go on. I think in every domain you have similar issues. One Python package missing, you cannot convince the administrators to install it.
Yes,
where is your vision in this? So would you say that's more already then in the Docker container prepared? Or is that still something where the application domain scientist needs to be on top of things?
Like, I think it's both. I think it's both, honestly.
Question, right?
No, I think it's both. Honestly, I think it's both. Python is becoming a really complex beast to work with. Like, we have many different versions, and in particular within like the machine learning realm, have support for Python 3.9 or what have you, but then you want some library in Python 3.12, okay, and you're not going to be able to do that, and you try to like puzzle together your little environment and what have you. So I think like in the end, really, if you want to provide, you could use the system for those kinds of things, but for that you need to really dig into container construction and understanding how you build them. And like that is a kind of a science in itself, like building efficient containers, understanding what libraries you put where in the stack, such that you don't have to recompile and build like a humongous container that contains some NVIDIA driver that is like gigabytes large or what have you. So my answer is that you need to do both. I think at this point, like it's naive to think that systems architects and systems designers could be experts in understanding the requirements. And I think that machine learning engineers will have to put up with the pain of like sitting down with people and really looking at the systems to define these containers. But this is like, I know this is a huge problem, I think.
All right, thank you very much.
People should try out Rust. Rust, guys, it's the future, okay? Get people to pay you to write Rust code, and you will have a good job in 10 years. Okay, good. More questions? Anything from the chat, maybe?
Anything from the chat?
I left a bit of time for questions, so we're still on time.
Yeah, we're on good time, and there's nothing more from the chat. So let's take a 10-minute coffee break, right?
Perfect. Thank you. Thanks for your time, guys. Thank you.
Nice. Okay, so thank you for this talk. So, as you have seen, noticed the first day, and today we have seen. Okay, so on our first day here, so we have seen there was some nice effort towards how to make this quantum computing effort more closer to HPC and how to do this integration together. And as someone who came from physics background or like a computational physics background where I was doing like density function theory, or you can call it like atomistic calculations, I'm used to this HPC environment. And then when quantum computing came up and with different use cases where they tend to say it in quantum chemistry use cases, so it was fun, okay, but how to do this still on a larger scale, especially I'm used to simulate systems that has a larger amount of atoms, which is like around 100 to 1000 and so on, while the use cases I've seen, it's small use cases on hydrogen atom, for example, and things like that. But before I start, so that was what I wanted to kind of disclaimer. So I came from this DFT background, still learning, of course, quantum computing, and where I can imagine it and hope like to see it as a DFT running with another accelerator. So the CPUs, the GPUs, but what about QPUs? Where is that? And the effort here is still in the making, and more comments are welcomed. And if you have ideas and so on, I'm glad to hear and collaborate on it. And there's some manuscripts related to this and available GitHub code as well. And I will go through these things. So when I start talking a little bit about what's going on right now in the area, so I have seen, probably all of you have seen this workflow where you have like a hydrogen molecule and do like what's called like a variation quantum eigensolver algorithm. and solve it with some ansatz and doing in some kind of loop between the measurement or the state preparation, which is in the classical computer, and the quantum computer, where you can do this kind of advanced algorithms that can calculate such interaction or potential energy surface for such a molecule in an accurate way, like the figure to the right or here. So that's great by itself. I'm impressed by this, and that's where I was kind of trying this hello world examples. But of course, this coming from more what they call it, like, quantum chemistry field. I'm more of a physics part, but then I was wondering when I was quite curious to see, how this can be also done in big physical systems, or you can call like solid state systems. So as I noted there, applying this workflow beyond small molecules to larger molecules or periodic systems can be difficult at the moment, but because so many qubits needed. And when I am talking about periodic systems, so just to give a little brief introduction about that, I'm not really sure how many of the audience online or here have worked a lot with these solid state systems, but I'm trying to make it as simple as possible. So periodic system can be, 0D, as you have seen here, to 3D. Or, for example, maybe you heard about graphene, the wonder material that had won a Nobel Prize like around 15 years ago or more. For example, this is considered 2D, or maybe you heard about carbon nanotubes, which is considered 1D. And 3D is when you have like a system that has molecules arranged in X and Y and Z, like those systems over here. One important system, for example, can be this metal organic framework. Probably maybe many heard about it because it has a direct application for carbon capture, for example. So this is a good one to see. Yep. So in a typical computational material workflow that has, you start with that you want to get a model like your molecules or systems, or called like supercell, where you can get the electronic structure out of it, and then there's many degrees of freedom, and so that's why you need to simplify your problem and replace these interacting systems with density. And density has 3 dimensions, X and Y and Z for the density. And this is what you can still consider it as an embedding downfolding. And at the end of the day, you want to calculate things related to this system. Okay, then it will be higher. Then you get a result like ground state energy or forces and so on. So that's kind of a typical workflow for this. As I mentioned for here, this embedding downfolding, it can be something like if you're coming from a density function theory background, it can be like more of the approximations that can be used to simplify your system. So just to give you a perspective about why this type of calculations are important or good, because I heard through the years some different percentages about how the HPC centers are busy with those kind of calculations. But there's some publications about numbers here. So I think this one is from UK, from Perlmutter, or I think US, I don't remember. Where you can see here a big chunk of the percentage, 11%, for example, coming from VASP, which is using this DFT methods. Berkeley GW, and you can see also espresso here, which I think is called a quantum espresso. And there's also similar classical means here, like GROMACS and LAMPS and so on. And I was amazed also that the GPU accelerated nodes has a big percentage for example, for espresso and VASP as well. So those calculations are important in HPC time. Also, I found this old chart, which is interesting, that trying to balance a little bit for you in VASP and CP2K, which is a code that I will be talking about in this demo, and other codes as well. And that was kind of some statistics from November 2011 to 2013 about what's the codes used and so on. So what I wanted to say here, that there's a potential to combine those two walls together, so we can still get the promised higher accuracy that we can get or from quantum methods, but also still the efficiency of using such classical hardware with classical methods like density function theory. And typically, if you're imagining what's called like quantum-centric supercomputing, so this is where it's many research teams and companies are taking this initiative, and also I've heard some talks about it in this school, where you can still use the quantum accelerators with the HPC infrastructure to do material simulation. And that chart actually was organized in kind of some phases, like you can call it like long-term phases, near-term, and real-time, which is still connected together, as we have seen here. But if you start from the left-hand side, so this is pre-processing, and then after that you call like active space, and this active space is related to the downgrading part I was talking about. And then you do the calculations, as you see here, for the real time, and then you update your parameters, and you use error mitigations and so on, and then get the final calculations. So what I wanted to elaborate here in the slide, so there can be a workflow to do this quantum simulations for material science, and practical-wise, you can have the atomistic structure on the left-hand side, as you see here, and then you go through what's called like quantum embedding theory. And in this theory, you have already your DFT calculation in place, but a small part of your calculation is done on a quantum computer. And the reason you choose a small part depends on the problem in choice. So, for example, if this problem, you know already that there are going to be some specific molecular orbitals that will be associated with an important interaction taking place, then you tell the system or tell your calculation workflow, you specify these orbitals that will be important to also study it using the quantum algorithm or using this kind of, different method. And this a little bit similar if you are familiar with a method called QMMM, where QMMM, it means molecular mechanics, and QM, quantum mechanics. Molecular mechanics, you can have a big system of like thousands of atoms, where there's a small part of the system that, for example, have interaction between like a small molecule within the system and the whole system. So this in somehow similar to this, which is called like embedding scheme, where you specify an active space, and in this active space, it takes into account all the system around it to be calculated using the classical density function theory. And in other sense as well, there was other people trying to make analogy for it with that the environment DFT is you kind of treat it as this something called like PCM models, where you can treat the environment or as one variable. You can, for example, you take the electric number of it. But for now, active space is that the small is a way to focus on specific interactions or specific orbitals taking in the interaction within your system. And then after that, it feeds through, you have this feedback from the active space electronic structure that is calculated with the VQE algorithm, and then goes back to the classical DFT code or the classical method that is fed in, or you can say it can correct the variables, forces, energies that are calculated by the classical part. So as I see highlighted here in blue, so this figure is kind of showing how to combine the classical and the quantum calculation using the quantum embedding method and large simulations. I mean here simulations that has big systems of calculations can utilize this using this active space approximation, and this of course will reduce the resources required to model the system. Of course, if at some point we have the luxury to run the whole system on an or using this, it can be done. But also, maybe you don't need that. So a little bit in theory for this. So this energy term is like describes the active space, how it can calculate the energies. And if you see here, it uses like the active space system, it's called like system A, and it can be embedded in an environment subsystem, and this environment system is like B, and you have such way to calculate it. And in sense, so if you see this block chart as well, then you do first a DFT calculation for the whole system, but you are only you are very interested in this triple bond dissociation that's taking place there on the right hand side, and then you want to describe it with a higher, more complex theory, which can take this in place. Then you partition your system into what's called like active space, which here is specified by blue, or this triple bond, and the environment around it. And the environment here is a whole other system. And then you rearrange your orbitals from the orbitals that are mostly involved in the interaction to the ones that are least involved in the interaction, and then feed these or do this VQ calculation and feed back the loop to the DFT calculations. And over here on the left, there's like more details about it. And of course, you can go to the reference to check more details. Also, I like this workflow over here, which this one, or the quantum embedding scheme, it can be done with several techniques or several methods. And one of the most efficient methods here is called adaptive UQE. And adaptive UQE is quite good for this kind of systems. It stands for Adaptive Derivative Assembly Pseudo-Trotter VQE, which is a technique that can build on the fly ansatz, which is kind of the starting point to describe your system from a predefined pool of operators or pool. And this pool is the tool is quite efficient in the terms of that it can well describe the systems, and you get convergency quite quick. And then you get ground state energy after it corrects for the parts coming from the specific orbitals that you are taking in place. And here is the workflow for that, where do first initial state and initial state ansatz, and then apply that, get a trial state, and then measure it, not converging. Then you go again to the pool of ansatz and repeat it again until it converges. And this different pool of ansatz, I can say that is offered by EuroCC, which is called stands for Unitary Coupled Cluster. Unitary coupled is a variation of unitary coupled cluster. And then after that, you can construct the initial Hartree-Fock and go on with the calculation. But hereby, I wanted also to highlight the point of how to combine this with, a practical use case. So we have seen today like a talk by Boeing, and yeah, they had talked about more of a optimization problem, but also I see that aerospace and automotive has other good application, which is related to corrosion for the body of those either aerospace or a car. And corrosion is an important problem because right now it's a corrosion industry. Corrosion inhibition industries use chromium-based coating materials, and the coating materials here is quite important to protect the body from getting the corrosion spread. But there is, of course, effort into replacing this because chromium has some environmental hazards and danger. So this is a big, quite important problem that if we want to model it using DFT, it can be done with some simplifications. Let's assume right now the problem in place is that you want to examine a new set of corrosion inhibitor molecules on top of this car body. Car body is most of the time contains aluminum alloys. So for simplification, you can consider it as just having like an aluminum, and you want to examine your corrosion inhibitor on top of that aluminum. So in this figure, I just wanted to show, how the mechanism is taking place where the corrosion inhibitor, where those molecules want to really bind to your surface and protect your surface. So that's why one important aspect or physical variable here can be to measure how this binding action will take place with a metal. So we want to measure how strong will this be binding. So before going there, I wanted to see the slide. Maybe the slide now is better in this order. So you can consider we're having this aluminum alloy and environment and the inhibitor molecule. But then if you want to describe this in calculation where someone came up with a nice new inhibitor where you want to really see the interaction with the aluminum surface, then you want to simplify it using DFT and just take care of the inhibitor molecule action here, and then do like a model aluminum substrate and inhibitor molecule on top. So if I go back to that, as I mentioned, then you basically want to build a DFT workflow and of course identify the important part where you're going to focus on, where you can use a quantum algorithm to describe the surface adsorbent interaction and let DFT or the classical method do the other calculations, which is related to the geometry force, calculating forces and energies associated with this action. And as I mentioned here, so I'm building like a hybrid quantum classical framework. Classical calculations are implemented classical codes like CP2K code and the quantum algorithm using implementation in Qiskit. So for those two walls to talk to each other, there was some effort that recently have implemented such connection between them, between these two different codes. Of course, CP2K is written in Fortran, and Qiskit is written in Python. And the part here that is doing the library from Qiskit that can be associated with these kind of calculations is called Qiskit Nature. So you need some kind of interface between them, and this interface we came up with an idea to connect it using Unix socket communication. Of course, this is nice that it can allow interface with such mature code for atomistic simulations, and that's a great effort. It can be also further enhanced. I can imagine if Also, the cascade part can be parallelized as well. I'm not aware of this, but it can be great to see it done. And please look at this literature. This is, I can say, this is the most important article to consider. But if we look more specifically into our problem, so our problem is just a better, a domestic problem point of view, where we are just introducing quantum simulation into it. So if you look from the left-hand side, you need to come up with other inhibitor molecules, and other inhibitor molecules, there is some databases online for that, and one database called Core Data, which is stands for collusion data, and screened many organic inhibitors for that. Here we want to use it for either aerospace or automotive. Then there's some certain filters you can do here. One of the filters was, of course, like pH ratios and temperature range. And of course, mostly important, small inhibitors, because those inhibitors can be huge molecules, but you don't want these kind of huge molecules to study them on a quantum algorithm right now. But when I was preparing the demo for that, I also suggested you can even use do this calculations, which is totally experimental, totally classical here, which is related to the geometry optimization and pure classical simulations. And by that, there is right now emerging field called like to accelerate these calculations called like ML potentials. And in that one, I used this model, which was introduced 2 months ago, and it's quite efficient to do a geometry optimization for periodic systems using this model. And of course, meanwhile, you need to prepare your surface alloy, or the aluminum surface over here, run it through geometry optimization, and then do your classical DFT calculations. And classical DFT here, you are doing it with CP2K. And it's important step here, because first you can benchmark with this method after you do your kind of hybrid calculation. Moreover, you can also use it to select orbitals that you need to calculate on quantum method. And then after that, you go to the hybrid part, where you have active spatial selection, and then you do your VQE calculation, and here, or adaptive VQE here, and then you are done. Practical wise, here's the system after being geometry optimized, and then here's the CP2K. Sorry for the small font, it's not so good here, or the resolution. And then CP2K here has this integration already, active space, and then you get your calculation done. So to give you a little bit more details, that was kind of the computation details for that, for whoever is interested in such details. Basically, I use also like dispersion correction is quite important here, because we are dealing with adsorbents or molecules with a substrate system. And then the binding energy is calculated through this formula. And of course, the higher the binding energy, then this proves that this inhibitor is not better than the other inhibitor, for example, in binding to that such surface. This was more detailed parameter calculations for you to set up your system, and the input files are already in our GitHub. And talking a little about results here, but maybe before we go to the results, I can quickly jump into the model, the demo. I had I tried to do it for everyone as a demo here. Unfortunately, it seems I needed to use a Docker image for CP2K. But right now when I'm talking, maybe there's already CP2K inside Loomis, and I don't know why I went this way, but I made like a run script over here that can install things for you, and also at the end of the day, it can also have this the Docker for the latest CP2K version, and then run. If you see here from this one, yeah, it's sorry, not a Docker right now, a Singularity, but I just pull a Docker container for that, and then run it and let this calculation be running. And meanwhile, I also run the VQE calculation over here, and I pass to it the 2 electrons and 5 orbitals to work on that. So, but if I here's another machine I have, and that's was almost the same things, but I'm using Docker here. So and if in this calculation, if I show you the log file, this is the log for CP2K. So CP2K started and is doing iterations to get the convergency classically, and then after that, here's the iterations, and then it got converged in 71 steps, and then merging local orbitals. Yep, nice. So until here, it's all the classical part, and let's see the active space. Yes. Okay, float. And this is active space calculation over here started, and then generating the canonical orbitals, and then right now it's using active orbit is choosing this 5 active orbitals to calculate the energy for them, and then used to hereby is a result for this iterations. And then it communicated back to CP2K and then CP2K close. Here's a Python output. It's also logging some information over here. In your calculations. And so on. It's also some iterations. And in order to have a look in the CP2K files, this is busy for DFT input, simple inputs, cutoffs, and so on, choosing the functionals. And then hereby, this is the part related to the quantum algorithm or the hybrid algorithm, which is only this one. Yeah, absolutely. So as you see here, you choose a number of electrons, number of orbitals, and some convergency things, and you choose the active orbital you want, or you let the code to choose the active orbitals for itself. Yep. So that's cool. So this calculation, I have done it already, but maybe I can do it again. So if I go here, CP2K log, then CP2K is having their iterations. This is still DFT, I think. And meanwhile, these input files are there in the demo, in the notebooks, but I will show you right now. One of the things that I have chosen a big system like this, 4x4x1, is because inhibitor molecule is not so small. So I needed to avoid the interactions between the different periodicity that's produced by the code. Meanwhile, also, in my opinion, it should be even higher because at the moment I cannot have a key point, a denser key point more than gamma point when the calculation is having an active space calculation. So if you can, for example, if you can make it like 8x8, it could be nicer. And then you can safely say that I would like to choose gamma point calculations, gamma point, key point sampling. Yeah, so here's conversion and done, the classical part. And then you can say the correction from the active space is coming in, and it is done right now. No, not done yet, sorry. Right now here, as you see, it created a socket, and it's called like embedding socket, which is this Unix-based socket that is doing the communication between the two worlds. And I think this will take only one iteration here, but we can go to the Python log and see that several iterations are going on here. This is, or you can call it like the adaptive EQE iterations. So this calculation is done for the supercell, but if you remember the binding energy, you need also to calculate for only the inhibitor molecule, the energy for the inhibitor molecule, and also you need to have a separate calculation for the substrate itself, and then do the math of subtracting the molecule energy and the substrate energy from the supercell energy. Yep. Okay, nice. Nice. So it's finished and gave the feedback already to the CP2K code. And then converge it. And then right now you have the program stopped already or done or completed. And you can grab the total energy from this output file, of course. So going back here, so after if you remember the first step when I was telling you here about screening different inhibitors molecules from a database, so again for the resolution. So I came up with those suggested molecules that maybe they are very good in this action for to be used in the two worlds, in aerospace and automotive. Yet have chosen the first two, which is almost the same, but the second one has a sulfur group added to it because they are small enough and quite still efficient, as we have seen here, 90 or 70 to 90%. Okay, let's say 90% efficient in doing the inhibition action. So shortlisted. There are two variations of the same, which is called triazole. And the results that is calculated from several calculations that I have just demoed to you is here. So, but of course, I wanted to calculate classical DFT binding energy with this adaptive VQE binding energy and with the vanilla VQE. And the reason I choose the vanilla VQE here, vanilla VQE here can take hours to do, and this is because of the initial ansatz that is not so smart enough to do all of this pool of ansatz that adaptive VQE is doing for us. That's why it would depend on the input or the user input for that. And you have seen here also that it's overestimated the binding energy, and maybe this is not correct for that. And the reason I'm saying here, because I already compared with a classical DFT, because the adaptive VQ should be a little different. But one note here as well is that the difference that adaptive EQ is introducing here is not so big from the classical one. And for that, I believe the active space should be bigger still. Yet I didn't manage yet to have the same calculation with a bigger active space, a larger active space, I can say, more than 5 orbitals. But at least the workflow converges and works all in all, and what's remaining is a lot fine-tuned, I believe. But at the end of the day, I wanted to also to present this as a material science problem. So that's why I try to focus also on the science and, and why the binding is happening and so on. But so as a conclusion here, I can say that this is demonstrating the kind of a hybrid workflow that can have the classical and the hybrid quantum algorithm together to solve a problem that is well known and quite interesting for the industry. Hereby, I have chosen a physical property, which is a binding energy to do the benchmarking. And I can still say that adaptive QE here is showing better performance and efficiency when it comes to comparison with vanilla VQE or the normal VQE. Active space is still a big thing here, and please check the manuscript and GitHub as well. But I can say that ongoing development is, as you've seen, is scaling to larger active space, and also the tools that I'm using here is that I'm integrating already, or I'm using like the Qiskit nature integration with CP2K, which was based on per version 0.46 Qiskit. Right now, Qiskit is 1.13 or 12, I think. There's some things I've made for that upgrade, but the newest version of Qiskit has a lot more potential to a lot more functions that can use in that workflow. Moreover, also I benchmarked here against DFT, but also more method, more kind of accurate methods like FCI can be in place here to demonstrate against it. Also preparing or choosing for specific hardware, the circuit ansatz can be important. And there was some recent work here that I just saw yesterday, which actually deals with a problem called bootstrap embedding, which is a little bit different sort of embedding. I can still think there's a little variation for these embedding schemes, but it looks like it has a potential to scale for 2D and 3D materials, as long as they say that, and they mention this as an application as well. But having this slide, I can also encourage to look at these resources. It's quite nice, and here's all these references. Yep. Thank you. Okay.
Yeah. So, do we have questions?
Yes.
Is there a question? No.
Yeah.
Hi. It's really nice to see like the quantum material science. Like, hello. Okay. What is the difference between vanilla VQA and adapt VQA?
It's more in the ansatz choice. So if we see this one, so with but please also audience correct me if I'm wrong. But this ansatz element pool that the adaptive VQE is choosing from is not available in vanilla VQE. Vanilla VQE, the answers you start with, you are stuck with it, and then you are waiting for the convergency self-consistent, or like
Que je pensais, il y a une structure qui est
give you convergency at the end.
Do you also update your answers in Adapt WikiWe?
No, you don't need. You don't need. You start with here by EuroCC, and then you are doing these variations in the background for you. And for me, as a kind of someone who came from this DFT background, I like to have something that can fix these things for me. It's nice.
And is it strongly correlated like this system?
No.
No. Okay.
No. It's like I don't think stronger. Because in what I understand about strongly correlated system, but also please the audience correct me, that we need to have high occupancy in the d orbitals. So we need systems like manganese or cobalt to say that they are highly correlated. So this one I don't think can be into this category of highly correlated.
And the last one is like,
absolutely.
So you mentioned your active space is 2 electrons and 5 orbitals. It's like if you increase more, like what will be the computational scaling? Like,
unfortunately, I don't know because the calculations were not converging with them getting with a higher number of electrons or orbitals. So this is something I need to solve.
And you have a vacuum in the system?
Yes.
How much is
it? Vacuum, as you've seen here. As we've seen here, between the aluminum substrate and the molecule is around 3.5, but then after that, 25 angstroms to account for the periodicity, because you don't. It's a slab system.
Thank you.
You're welcome.
Okay, any other questions?
Yeah, I know, for example, there is integration already between PySCF and Qiskit, which is quite great because the two of them are Python already. But as far as I know, but my information is old by 5 months. That the integration, the package that doing the integration between PySCF and Qiskit nature does not support periodic systems like this one. But the new package that I just showed here, this one, Bootstrap embedding, they support connection with CP2K, and in GitHub, in their GitHub, they say that they also support 2D and 3D systems, so it should be done. But also you go for CP2K if you need CP2K for some specific things. Of course, it's car-parallel block dynamics based, and if your problem needs CP2K, then especially also CP2K has a very good interface with different basis sets that you can get a lot of information for your system. So it's great to have. You're welcome.
We have one question from the chat.
Mm-hmm.
What is the advantage of EQE and the combined classical and quantum method versus classical methods with machine learning and neural network force feeds?
Yes. So because maybe the one who asked it, I've seen here in the workflow that they mentioned a little bit about ML potentials. So this effort, as long as other efforts seen, or these efforts that I've seen in the domain, they are made that to have a working workflow for this to happen, and then when we can scale our problem, we can speak after that about advantages and things like that. But for now, theoretically, you are still using kind of more computationally expensive methods like EuroCC together with DFT here, while machine learning potentials, we are using DFT because machine learning potentials are based on DFT or are trained on DFT. And also you can combine them with DFT codes that's right now as well. Like there is some implementations in VASP and there is some implementations in ASE as well. Yep. So yeah, we are not talking about advantage, disadvantage, but we're talking about the, applicability.
Okay, thank you. I think for time reasons, we should now have a quick break. We're a little bit behind schedule, but that's okay. And we'll come back with a very cool talk about quantum extreme learning machine. So 10-minute break, I guess, until 15 minutes past 3. See you then.
Nice.
Okay. I'm very happy here today to discuss about one of my work is using the quantum extreme learning machine on some case studies of software engineering. My background is software engineering. So I think today's talk mostly I will introduce a bit about the industrial background applied in these papers, and also some applications and mapping of the quantum extreme learning machine. Okay, let's go first. So our first industrial partner is the Orona company. Orona is one of the largest elevator companies in Europe. It has more than 250,000 installations all over the world. And a system of elevator, it aims to transport the passengers as safely as possible, whereas we want to minimize the time that the passengers need to wait for the elevator. And the core of the elevator system is a dispatching algorithm. It is used to schedule the elevators as optimally as possible by assigning those elevators to the passengers for their each core. And just like a normal software, each software they need to go through the regular maintenance and the evolution, the same as this dispatching algorithm. So if we want to upgrade to a new version of the dispatching algorithm, we need to involve the regression testing to ensure the high quality of the high code quality. Yeah. So Orona nowadays they have implemented 2 levels of testing in simulation. The first one is software in the loop. So it's a domain-specific simulator called Elevate, and the second one is hardware in the loop. So they need to involve the actual hardware components, something like the real-time operating system or human-machine interface to do the testing. And in the regression testing process, the inputs that they use is the passenger profile. It includes those passenger informations with a lot of attributes, and also has a quality of service of metrics. It is used to anticipate the value to test to see the quality of the elevator. And if we want to get the value of this quality of service metrics, we need to rerun the testing, rerun the elevator in with a different algorithm or a previous version of the elevator to get our quality of service values. So this is our challenging of test this elevator. It's like the cost of re-executing is very big, especially if we want to involve this hardware inside. Then it will be very hard to, like, the cost is very big. And there is another point, is like the elevator should be in service. So when they are in service, it's very impossible to re-execute any test case at the operation time. So we have a need that they want to use some machine learning based models to predict the quality of service metrics and to replace the regression testing oracle. And currently, Orona has developed one of the classical machine learning approach called Dario. It uses the passenger traffic data as the input to train the model and use the QoS metrics that collected before as the output value. So the passenger traffic data, they are extracted from those passenger profiles for a time window of 5 minutes. So they collect the information of the passengers in each 5 minutes. And the QoS metrics that we use is the average waiting time among these 5 minutes for all these passengers. But there are still some challenges because if we want to train the machine learning model, so we need to input several features inside for training. But if we want to test the elevators in different buildings, their installation configuration are different. And so some features, they are not all available on all these elevators. And also during operation time, there are also some features that we are unable to obtain. So this gives us challenges as the number of features that can be used for training is very limited. So in our work, we explore the solution, one of the promising solution called quantum extreme learning machine. It is a quantum machine learning algorithm, and it maps the classical data into the high dimension quantum space, use the quantum dynamics of the quantum reservoir. And this quantum reservoir can enable the efficient machine learning training with fewer features, while we still maintain the good prediction qualities. So this is the approach that we propose called QuIRE. And the quantum extreme learning machine is a gate-based algorithm, and it has both the classical side and the quantum circuit side. Here are the gates that we mainly use in our paper that I will introduce, and mainly we use this rotation gates to encode our classical data into the quantum circuit, quantum state. So before I introduce this quantum extreme learning machine, I will first introduce their classical counterpart. So the classical extreme learning machine is a feed-forward neural network. And it's like as a normal machine learning algorithm, we have this input layer to input classical data into it. And then, but the different part is this hidden layer. For this hidden layer, those bias and the weights inside that activation function, we don't need to train it because they are fixed and we are randomly assigned these values. So the only part that we need to train is this output layer. So we only need to train these weights inside this output layer, and this layer is always it's usually a linear regression of simple machine learning algorithm, such as this linear regression to predict the target value t here. And now we go to the quantum extreme learning machine. So the difference is that for the quantum version, we replace those quantum neural. We replace those neurons into a quantum circuit. For example, we replace this input layer as encoder, the classical encoder circuit. So we feed these classical data into the encoder circuit to transfer these classical information into quantum states, and the output of the encoder goes into the quantum reservoir. So these parameters of the reservoirs, they are also fixed but randomly assigned. So we don't need to train the parameters inside this circuit. And the last part is measurement. After we go through this encoder and the reservoir, we measure all these qubits to get this output vector. And use this output vector, we can predict this final output t with a linear regression model. So here is the encoders that I use. So I use two kinds of encoder. The first one is undetermined hardware efficient encoder. So it uses Rx gates as the beginning of each qubit, and then I apply those cyclic control Z gates to entangle all these qubits. And the second one is random hardware efficient encoder. So the difference is only this the first poly gates, the phase gates. We randomly choose these RY, RZ, or RZ gates to apply at the beginning of the encoder, and then we encode the classical data into the parameter, into the angles. And so the encoders, they can process this input data by parameterizing those rotation gates. And take this passenger traffic data table as an example. Here, this T/W shows different time windows of 5 minutes, and this F means different features that we obtained in each time window. So, but in order to avoid the values being encoded in the same state, so we need to use a min-max normalization to scale the feature values in this passenger traffic data table. And after we do the normalization, we input all these. We input one row of these features into the encoder and to transfer them into the quantum state. And here is the reservoir types that we use in this paper. The first one is the C-note reservoir. So in this reservoir, we only have this control X gate, so it doesn't have any parameters that we need to tune. And the second one is the hard random reservoir. So this is simply a unitary operation, but the parameters of this unitary operation follows the distribution of the hard measure. And the third one is the Ising reservoir. So it is made up of the single Ising Hamiltonian with a random coefficient. The last one is the rotation reservoir, and it has a similar structure with the encoder. It's also a hardware efficient reservoir circuit. And but the difference is that those rotation gates here, these parameters, they are randomly fixed and randomly assigned. So now we can go into the overview of this approach. The approach, it contains two phases. The first phase is the data collection. So according to the real operation and some theoretical files produced by the simulator, we can generate this passenger traffic data. And according to these domain experts, they can provide the features that we want to achieve from those passenger traffic data. And meanwhile, we can input those passenger traffic data into the hardware in the loop and the simulator in the loop of the dispatching algorithm to produce the quality of service, which is average waiting time. And in this query phase, we first normalize those feature values and input them into the QERM model. And after we measure the circuit, we can get this output value and predict the the average waiting time. And we use this obtained performance data to train the model. So now we go into some research questions. The first one is like since we have used like 2 kinds of encoders and 4 kinds of reservoir circuits, so we empirically want to know which kinds of combination of encoder and reservoir can achieve the best prediction with this with a different number of features. And the second research question is we want to see with the optimal combination, which is the smallest number of features that we can use to achieve the good performance. And the third one is we want to compare our quantum approach with that classical machine learning algorithm Dario. Here is some experiment setting. So the data sets we use, there are 4 days passenger traffic data we extracted from the real operation of elevators installed in a 10-floor buildings with a time window of 5 minutes. And here are the features that we use. And they include some, these features, they are related to the number of calls from different directions and different floors. And these 2 features are related to the average distance of traveling of this elevator. And these 2 ones are related to the number of calls in the past. But as we have mentioned before, because of the various configurations of elevators and also if we want to achieve the features in real operation, it's very difficult. So we create different feature sets to train our QERM model and to evaluate our performance. And so we ask those domain experts to create these 6 feature sets. For example, for this FS2 means like we only have 2 features for training in this QERM model. And okay, and there is the QX matrix. Okay. And next is our baseline. So Dario, it uses the SVM and the regression tree models. So we compare with these 2 algorithms. And the quantum environment that we use is a Q-reservoir package. So we run our experiment on an ideal simulator. And the evaluation metric that we use is the mean square error of the predict average waiting time. And in order to avoid the randomness in the experiment, we repeat 30 times for each experiment, and we achieve this average MSE value to do the evaluation. And we also conduct some statistical tests. Yeah. And for RQ1, we want to find out which combination is optimal. So here is the violin plots that we draw of the average MSE value achieved by each combination, and in these 24 settings. So if in each violin there is 24 data points, and these 24 setting refers to these 6 feature sets and 4 data sets. So we mix them together. And according to this figure, we can see that these 3 combinations, they always achieve better values comparing to other combinations. And furtherly, we want to know their performance, so we rank those combinations for each setting, and we count number of times that they get from the top 3 orders. And according to this figure, we can see that this DHE eSync combination, it achieves like 12 times for the first, the top performance within these 24 settings. So we can empirically get the conclusion that to this data set, this eSync reservoir combined with this DHE encoder can enable the choir to perform the best. And here is our second research question. So we want to see the number of features that can achieve the good performance comparing to the maximum number of features. So so here is the violin plot of those performance of these MSE values, and this y-axis means the MSE value, and this x-axis is the different feature sets. So the maximum number of features is 10. So in our training, mostly we use 10 features for training, and the others they are like 2, 3, 4, 5. And the results, because for it's this MSE value, so it's the lower the better. So we can see that this with the 10, it is not getting like better performance comparing to others. And also we did some like statistical tests, and we can get some similar conclusions that we can still use a smaller number of features to get the comparable performance with all these features. And so this is our conclusion that we can use the fewer features can outperform the choir with a maximum number of features 10, and it shows the effectiveness of the QER in our industrial context. And the last one is like we want to find out how well choir can perform compared to the baseline. So the baseline is Dario with 2 machine learning models. So we also train them on these 6 feature sets and 6 feature sets and the 4 data sets, and we perform this statistical test, and the results show that there is significantly difference between our approach and the machine learning algorithm. And for further, we perform this coherence effect size to see the magnitude, and the results show that our approach is significantly better than the 2 classical algorithms. So yes, so this is our conclusion that for the same prediction task in our industrial context, choir can outperform the classical machine learning approaches, and it also demonstrates the potential of the QERM algorithm. And here is our lessons learned. So according to these results, we can see that in the future, we can apply these QERM machine learning model into the runtime prediction, and also maybe to build the digital twins for these elevators. And we can also apply this QERM model in other prediction problems in other contexts. And there are also in some research implementation, it's like this approach, it opens up the direction of combine both classical and quantum software engineering, and we can also see that we can use some empirical study to see the performance of different configurations in the quantum approach. Yeah. And here are conclusions. So the main takeaway from this paper is like QERM can offer better benefits by performing the significantly better prediction with even fewer features. And our previous work is related to the idea simulator. So we also want to know that how is the performance of this QERM in practice. And so here is our motivation. It's like, so because the ideal simulation, it does not reflect the reality of with noise. And if we want to simulating this large-scale industrial problem, it's very unfeasible because of the running time and the cost. And also the application of QERM in real world with noise is rarely explored. So we propose this this work. We evaluate the impact of quantum noise on QEM models through the 3 industrial real-world case studies. And we also assess the feasibility of combining the QERM model with some noise error mitigation techniques to enhance their applicability. And here is some background. So this talks about the source of quantum noise, and I think it has been talked yesterday. So it's, for example, they have some sources like decoherence, crosstalk noise, and hardware collaboration errors, and something more. And then I will discuss about 2 error mitigation methods that we applied in this work. The first is non-machine learning error mitigation. Is this zero noise? Is a CNE approach? It is also have been discussed, I think, yesterday. So the main core of this approach is like we first intentionally scarce noise model the noise by some approaches such as applying additional gates, and then we apply some mathematical approaches to anticipate the quantum state with no noise. And second one is machine learning error mitigation approach. It's also like proposed in our department called CLEAR. And in this approach, we first extract the circuit level features and also the output level features. Then with these features, we train a machine learning model, noise model based on them to get the ideal output without noise. And then I will discuss about some case studies, some more case studies that we involved in this work. The first one is Oslo City healthcare data. So the healthcare department of Oslo City provides some healthcare service to all the residents in Norway, in Oslo, and it has a healthcare IoT-based platform that connects some medical devices with some pharmacies and patients. And these medical devices, they are like allocated to different patients in order to enable some real-time alerts or personalized cares. For example, this medical device we show here is called Carry. It is a medicine dispenser that it can warn people to take their medicine and produce the medicine to the patient. But if we want to test this healthcare IoT application, there exists some challenges. It's because the system level testing of this IoT healthcare application, it will involve multiple medical devices. But using them in tests will lead to the devices being damaged or even service blocking. So in order to test this healthcare application safely, we propose one of the approach is like we use a digital twin, a machine learning based digital twin of this healthcare device to and then we use this digital twin to facilitate the automated and testing. So in this testing process, we first use this testing tool called EvoMaster to generate the REST API tests, and then this SUT will this healthcare application will communicate with digital twins with API calls, and based on so in this after we build this digital twin. we don't need to use these devices so much is because the healthcare system only communicate with the digital twins, and these devices are only used for the calibration and the synchronization. And in our work, so we try to replace some part of the digital twin inside. So we based on those data sets that we collected from the digital twins of Carrie, we train the QERM model to predict the responses, like it's the HTTP statute codes to support the automated testing. So in this model, we collect like 18 features, such as this brightness setting of the device or like language preference and something like this. And then the output of the model is HTTP statute codes, state codes, like the 200 or 500 something. And so for this work, so it's a classification problem that we implement. And then we go to our second case study is Norway's cancer registry data. So cancer registry of Norway, it collects the cancer cases across Norway by receiving the cancer messages from the different healthcare institutes. And these cancer messages are validated by a set of rules by an automated system called CARES. And CARES can also, it can collect these messages. It can also analyze these data and generate the statistics for those policymakers and healthcare stakeholders. But there are also some challenges for testing this care system. It's because like when we want to test them, each request sent from those testing tools, they are running in real time. It's because like we cannot stop using this care system. So if we, when we test them and execute, but if we meet some invalid requests generated by those testing tools, it will incur a lot of unnecessary execution costs, and also it will impact the performance of the care system during the operation. So we also propose one of a machine learning approach called EVO class. So this approach is testing tool that is a machine learning based approach, and it is proposed to filter out the test cases that are likely to be invalid. So it's following the same process that Evo Master first generates this API test, RESTful API test, and then we use this Evo class to filter out those invalid requests. And so based on this data set we collected for building this Evo class, we use this QERM model to try to also predict the potentially successful or unsuccessful tests. So the input for this scenario is like we have the 57 features, such as patient medical records or cancer types, to input into the QERM model, and then we predict if it is successful or if it is success or failure. It means if this request is valid or invalid, and then we will filter out those invalid messages. And so it's also a classification problem. And the third one is, as the one before, is the Orona system. So the different part is like the Orona system is a regression problem. It's not a classification problem. And here is our research questions. For the first one, is like how resistant is QERM to this quantum noise. So we want to see that if this algorithm is like it can be noise tolerant. And the second research question is, how effective are the current practical error mitigation methods to these QERM models? So here we go into our experiment setting. We first select the key features based on the feature importance score. It's because there are like so many features, we cannot fit all of them into our quantum circuit. So we use some machine learning ways to extract some key features. So it's like we get these 3, 4, and 8 features for different data sets. And the noise model that we are running on the noise simulator, and the noise model we use is these 3 for these 3 real quantum computers from the IBM. And then we also compare our approach with the baseline in this table. So in this table, we first evaluate in these 3 data sets, which is the base combination of the reservoir and encoders. And as the same before, we find that this is DHE. DHE and eSync combination is the best, and also we combine them with a different simple machine learning model as a output layer to predict the output. And the metrics that we use for these 3 data sets is like MSE values and accuracy. So it's like for the MSE value is the lower the better, and accuracy is the higher the better. And we compare our approach with the baseline, and the baseline is a classical machine learning model that we proposed in our previous papers. And the results show that in the first 2 cases, in the first 2 scenarios, it's like our approach can outperform the classical approach. However, in the third case, we cannot outperform the classical approach, but it's almost comparable. So we can get some conclusions that we still can use this. We can trust this QELM model on the ideal simulator. And now we want to evaluate its performance on the noise simulator. So we first draw this box plots of the 10 runs of each dataset on the 3 noise models. So in our experiment, we have two scenarios. The first one is like we adding noise both in the we adding noise only in the testing phase, and the training phase is only on the ideal simulator. And we can see that the y-axis here shows a change from the ideal values percentage. So we can see that the performance is really bad in this case. And then we also go into another scenario. It's like we add the noise both as a training and testing phases, and we find that the performance is like improved in some cases. So we can get the conclusion here is like noise in both training and testing phases can reduce its impact and on the model performance. But we think like error mitigation is still required for the practical use, since the value is still not very good. Okay, so now in the second research question, we integrate our QELM with this error mitigation approach. So the first table shows the performance of the ZNE approach, and the second table shows the performance of the CLEAR, and CLEAR is that machine learning based approach. And these values in the table shows the median among these 10 repeats of the percentage change from the ideal values. And these bold values here shows that the error mitigation, it can significantly improve the performance. So we can see like we only need to like focus on these 6 columns. There we are putting the noise, and we are applying both noise and error mitigation at the training and testing phases. And we can see that for this ZNE, only with this phase quantum computer, and also with only these 2 scenarios, it can achieve the significantly better performance. So we can get the conclusion that ZNE, they are constrained by the qubit size and the noise models. And constrained by the qubit size is because for all these 3 datasets, we are using a different number of features to map. And the next table, we see like in this machine learning based approach, it can excel in these 2 cases because they are all in board. They are all be significantly better than without the error mitigation approach. So we can get the conclusion that it can outperform in these 2 cases because they are all classification tasks, but it fails in these Orona cases. So we can get some conclusion. It's like integrating the error mitigation methods. It can enhance the noise resistance of the QELM, but their effectiveness is still very context dependent. Okay, And here we go to our lessons learned. For the QELM application side, there is potential that it can outperform some classical machine learning models, but it still has some scalability issues due to the quantum noise and the qubit limitations. So we require solutions like some error mitigation approaches. And in the practical limitations, it's like real quantum computers and the effective error mitigations they are required for the larger size of problems, but it may still introduce some significant computational overhead because of error mitigation. So we think like QERM models, they need this tailored error mitigation strategies, maybe to be valuable for some spatial fields. And here is our conclusion. So the main takeaway from this work is like we know that error mitigation can enhance the noise resistance and in the QELM model, and also these tailored error mitigation strategies for the QELM, they are still needed to enhance their applicability. Yes. Okay. Thank you.
Hi. Thanks for the talk. I have one question about the noise and how it relates to quantum extreme learning machines. So basically, if I understood correctly, at the end of the quantum circuit, we add a feed-forward neural network or any kind of neural network. Could it be that the neural network already learns to mitigate some of the noise and to filter out basically the noise?
You mean like in the training side, we also put the noise inside, so when we train the QELM model, it can learn some noise patterns?
Exactly. So you don't really
Yeah.
need to mitigate it because the noise is implicitly mitigated through the feed-forward neural network. It could, for example, learn some kind of confusion matrix.
Yeah, so this is our like original assumption. Like we think that QEL model can like learn some noise patterns, but the thing is, we find out that the result is still not very enough for the real application. So we want to apply some error mitigation inside to see if there is some performance improvement, and we see there are some performance improvements in some cases. So we think it can, maybe if we can create some better quantum QERM model, maybe it will have better performance in the future. Yes, but currently for this work, I think we still need this error mitigation. Yeah.
Okay, thank you.
Thank you.
Yeah, thank you very much for your talk. I would sort of agree with the gentleman before that isn't it like a regularization effect with the noise, but that's not my question. I think in a way, neural network should maybe deal with this. But my question was, we always think like quantum computing will be also a more greener way of computing, for instance, compared to HPC. And I noticed that you always had one selling proposition, let's say to your customers or so, that are in the area of mean square errors, accuracy, lower error rates, whatever. But you never took the time to solution, for instance, which in our quantum devices is quite significant. Just my question, I think I'm asking is it so little compute that you don't care with scikit-learn and your trees you do through your baseline models, or why you never consider the time to solution or the resources you needed for the quantum device and for the baseline model to compare?
Oh, it's because in our current work here, we haven't involved the real hardware inside. We are just doing some explore some theoretical potentials. Also, they are all on the simulators, and so we assume that if we have real quantum computer, it should be very fast. Still better because the training should be faster than the on the computer, but I don't know, like if maybe for HPC it's also good. Yeah, but it's a very valuable point. Yeah.
Mm-hmm. Okay. Yeah. Thank you.
Hello. Great presentation. So since you've done ZNE and QLear, which if I'm not wrong are both they both operate on just the gates. Are you planning on like integrating readout measurement as well, readout error mitigation? Because as far as I'm aware, you should be able to chain readout error mitigation with both of these techniques.
Redundant. Redundant what?
Read out error mitigation.
Read out error mitigation. I'm not an expert in error mitigation because this work is done by my colleague. So I think I can give him this suggestion. Yeah.
Yeah, because you should be able to chain that with. I know for a fact you can chain that with ZNE, and I think you should be able to do that with QLear as well. So hopefully you get better results.
Okay. Thank
you. Yeah, so I will talk about Tajite. It's a software stack for the quantum computer at VACT at Chalmers University. And my name is Martin Ahindura. I'm from Chalmers Next Labs. That's a subsidiary of the Chalmers Group. Yeah, and I'm happy to be here. I'm blessed to be here. So, what is Tajite? You can see on the left, that is, we have this nice lab. You're looking into a lab right now, and that's the VACT quantum computer. We call it CAL 9000, at least in NordIQuEst, it's called CAL 9000. And we need, it requires some software to be able to do what it, okay. It requires some software to be able to do what it should do. And so this is why we built Tajite. So Tajite is just a collection of multiple software components loosely connected, and it is responsible for making the quantum computer available to multiple users. So it gives multi-user access via the internet. So it can be used by many kinds of users. So we have the normal user who would be able to, say, submit quantum jobs through it. Normal user can retrieve the results of the said jobs. The user can also see the device parameters of the quantum computer. I think one thing that I should mention, why we are why we're trying so hard to build a VACT quantum computer when we have the IBM cloud service and the like, is we want to give low-level access to researchers like the people in here and the ones online, so that you're able to see as much as you can into the systems you're using. They're not closed. We want to make everything available to you, all the device parameters that we can give you. And so that's one of the things that is driving, that is motivating us. So that's why I had to add that low-level access. But then it's not only for you, the users, we also have an option for the people who are doing the maintenance and the servicing to be able to recalibrate the device through the internet, so that they can do this over the weekend at home, seated watching whatever favorite team they watch. And then also to be able to turn on and off the device remotely and monitor it, the temperature and pressure and the like, and also to be able to manage user access. Yeah, so that is what Tajite is. And now what can we do with Tajite? What can you do with Tajite? As I said, Tajite is a collection of multiple components. They are loosely connected. They can be used. They work together well, but they can also be used individually to do like single tasks or things. So one of them is the Tajite. It's okay, on PyPy you will find something called Tajite. PyPy is the Python thing that tracks Python libraries. I hope you all know it. So we have an SDK, a software development kit called Tajite, and you can use it to connect to the VAC quantum computer that I showed you earlier. But so that you use it in your notebooks and the like, almost like how you use Qiskit to connect to IBM. And then we also have developed a calibration library. I think my colleague yesterday talked about it. It's called Tajite Auto Calibration. So you can use it to calibrate your own quantum chips. The caveat there is they need to be of the same design as the VAC quantum chips. And then if you have maybe your own quantum computer somewhere, you could also decide to make your quantum computer available to many users through the internet. And so you can use the Tajite backend and the front end to expose it. So Tajite is free to use. It's open source. It's on GitHub. It's under the Apache 2.0 license. And we are trying to be as active. We actively develop it as much as we can. So we have a quarterly release cycle. And I think this month we have one coming up. So how does Tajite work? I am not going to bore you with the minute details of how it works, but I'll just try to go through since it's an overview, just the top view. So it's a collection of different software, as we said, and one of the components is the Tajite backend. And the Tajite backend, as you can see on the right, I guess, is run on a server somewhere in our lab, and that server is connected to the control instruments. We use Q-blocks. We use Q-blocks clusters, and then that cluster is the one which is connected to the quantum chip, and it's the one which sends the pulses. So the backend is responsible for converting the instructions from either the user or from the calibration tool. The backend converts those instructions, we use OpenPulse, similar to OpenCASM. So we use OpenPulse to communicate across the stack. So it receives those instructions as OpenPulse and converts them to something that our cluster, the Q-blocks cluster, can understand. And it's also responsible for queuing the jobs, because the quantum computer can only run one task at a time. And so you need to be able to have multiple, you need to be able to receive multiple jobs at the same time, but put them in a queue so that they can be run one after another. And then it also is responsible for tracking the device parameters. So it is the one which runs the calibration tool, extracts the results from the tool, saves them somewhere, and makes them available to the rest of the stack. And then we also have the front end. The front end is the thing that makes the cloud service, if I may say. So it is not needed for the quantum computer to be used. You could only have the back end and you're good to go. But without the front end, then you can't control access to your quantum computer unless you use something else, a firewall or something. So the front end does many things, but one of the important things that it does is to control access, user access control. And of course, it exposes it to the internet. It's the thing that is online right now. and it comprises of two things. We have a REST API. Now this one is it's for programmatic access to the quantum computer, and it, as you can see on the right, that's just a screenshot of the endpoints that we have, and it also has a dashboard. Now the dashboard is more for the human beings to interact with the quantum computer. I think one thing that I must note is the dashboard does not have everything that the REST API does, because we understand that there's some things that are better used in the terminal or in scripts than in a graphical interface. And then the other one, which I talked about earlier, is the software development kit. It's in Python. It's you can install it with pip, as you can see, and it's also Qiskit based, as we'll see somewhere. It's more like you're using Qiskit, but not connecting to IBM. You're connecting to Carl 9000. And then we also have the calibration tool. It's also installed with pip. It's a CLI. It has some fancy features which I myself, I don't even understand, but yeah. So how does Tajait work? Collectively, I was just talking about each. So on the right, you can see, we can see that bluish envelope. That's where Tajait is. So the SDK runs on the developer machine, so developer or user machine. So the user installs it in their virtual environment, and then the front end, we host it on a server somewhere on the internet, and that front end is connected to as many backends as we want. So we can have as many quantum computers, just like IBM does. We can have as many IBM quantum computers behind that front end. Then the back end is each back end running on a server is connected to one quantum computer. And so you can see that the SDK will send instructions to the back end, open pulse instructions, and then from the back end to the control instruments, we see some, I put here microwave instructions, but more of cube block specific instructions. And then from the control instruments, the pulses are sent to the quantum chip. And then the authentication and basic device data is all in the front end and a bit of the back end. So if you wanted to test it out, where would you go? So we are still in the process of assembling the physical quantum computer at VACT. So we can't say it's live right now, but we have built sort of like a dummy staging environment thing. It's right now at Carl 9000 at that link. Please do not bombard us with too many requests. We are still in the experimental phase. But anyway, if you try to even connect there, you will probably be met by a login screen where you can't log in. But if you want to test it out and you love these things, you can go to GitHub. On that link, we have a quick start tutorial where you can run the whole stack on your own local machine. And there there are simulators inside, so you can run it with simulators or dummy clusters and the like. And that's what it looks like here. Fancy, right? So we're going to have a demo of how it will work. I am hoping that it is working because this is experimental. So we go to this site. I already visited that. I will log in. Yes, it's working. So it looks a little bit like this. I'm going to run through quickly so that you don't see the bugs that we have. Yeah, so basically, okay, there is this thing that's hiding behind, okay. Yeah, select a project, blah, blah, blah. Okay, so I'm going to try to run a simple job through the through the CAL 9000. I have a collab somewhere. I hope I find it. Yes. Is it visible? Okay. So it says first visit the dashboard. We've already done that. And then it says generate an API token. So for you to access the quantum computer, we need to be able to verify that you're who you say you are. So we use something called API tokens, which I think are very common. So I'm going to generate one. I've generated one and copy it. I should have started this. Oh, okay. I am on a video. Where is this thing? Okay, I think it's here. Yes. Forget everything you've seen. Okay, so I already installed Tajite, but it shows it works. So I copied the API token. That's the one. And then just save those. This is the API, the URL to our public API. And this backend, I guess I did not show you. There are two backends. I've chosen this one. This is the simulate. Oops, why? I need to close this. Okay. Yes. So this is the backend we are going to be using. It has just one qubit. So yeah, do the normal things. Create a simple Qiskit circuit. Initialize the backend with the API token. It's warning me, but I hope it will work. Yes. And then compile and run it on the back end. So the job has been submitted. These are, I guess, common normal Qiskit things. Backend run, blah, blah, blah. And then we're going to just poll for the results. Hopefully the quantum computer is the dummy quantum computer is running. If it's not, yay. Okay, so the results are there. I don't know if they are right. I have zero quantum knowledge. Does this look right? The circuit was this. XHH. Okay. Okay, yeah. So my colleague says, yeah, my colleague says that it's workable. It's in the range. Yeah. So this is how we can do it. So the computer is down in Gothenburg, and I am here, and I can do anything with it. Yeah, I guess that's it. This is not my own work. I didn't do it alone. I didn't even start it. I found it there. But this is all that the people and companies that have contributed to it. And if I still have some time, I can go a little bit under the hood. Do I have some time? Do I still have some time? Okay. So just a bonus for those who might be interested in this stuff. We'll just go under the hood and see what's happening in the back end. So the back end is just a Python application. It does many things, but a few things that I can note down is we have a first in, first out queue for now. We're thinking of adding book time slots or something. But for now, we have that first in, first out with Redis under the hood. We work with simulators that are based on Qiskit dynamics. And this month, we should be releasing a 2-qubit gate simulator. And then the compilation is to quantify schedules. This is, okay, we use an open source package from QBlocks and Orange Quantum, I think OrangeQuest. Yeah. And on the right, you can see I tried to just get the meat within the back end. So this is just a diagram of what would happen when you send a quantum job to the back end. So it comes in open pulse form and it hits the REST API endpoint. So the backend also has a REST API. So it hits it, then it's transferred to the queue, the jobs queue, where it's put on the queue. The job is put on the queue. The queue has 4 workers for now. So the first worker just puts it on the queue, saves the metadata in the database. And then the preprocessing for now is doing nothing, but we hope to add something. And then the execution worker is the one which does the main thing. So it's passing the open pulse instructions into the instructions that QBlocks would understand. And then it sends the instructions to the cluster, to the QBlocks cluster. And then the QBlocks cluster does the needful, it returns the results. Then the execution worker transfers the job with the results to the post-processing worker. Now this is the one which is responsible for discriminating, for state discrimination, if there is need for that. And it also saves the results in a database somewhere, and then it sends the results to the other part of the stack, that is the public API, from where they will be picked, as you can see. Now the public API, the thing that you see, the cloud service, if I may say, is this part. This is what I will talk about, I guess, here. A few things to note. It uses Auth2. And the API tokens that we use, that I picked, I think I should actually quickly do something here. Sorry. Just for security. I know someone might be sharp in something. So the API tokens are revocable, as I've done. I've removed the token. So, and their lifespans are extendable. Yeah, and access is project-based. So for you to connect to the quantum computer, you have to belong to a certain project, and the API or the cloud service will monitor the usage so that when that project, each project is allocated a given amount of time on the computer. So when that project overruns its portion, it's cut off. people who are using tokens that are based on that token will not be able to run any jobs. And yeah, and we also worked with Puhuri under the NordIQuEst project to connect it, connect our stack to Puhuri so that it is monitored and it's also can be provisioned together with an HPC or something like that. So on the right, you can see just a brief description of the main part of the cloud service. So this is the RESTful API. So the user initializes the quantum job, experimental quantum job using the SDK and sends the data to the API. And then the API passes that over to the job service, which is responsible for generating a unique job ID, saving metadata to the database and the like. And then the user will try to poll for results from the REST API. But the results come from the backend. So before they come, that's why I think you saw that message, not yet, not yet, not yet. So when the backend is done with the job, it will send the results to the REST API, which will then save them somewhere and then make them available to the user when that user wants them. And these are state discriminated results. For the bigger jobs, we also have an option of extracting the files directly from the backend. Yeah. Oops. Okay, that's it.
Yeah, thanks, Martin, for the talk. My question is basically, how do you do end-to-end testing? Basically testing the whole software stack. And you basically have a dependency on qBlocks Quantify. Were you able to basically decouple most of your backend so that you don't have to rework your whole software stack when Quantify doesn't update? Yeah, those are my two questions.
Yeah. End-to-end testing. So for now, of course, we've not yet finished, but for now we are testing it. We have written some few bash scripts and the like, but we test the whole stack in some on Docker, Compose, and the like. So we run the front end in Docker Compose, and then the back end is also running some virtual machine. Then we do the end-to-end testing. But we are fully dependent, at least for now, on whatever is happening with Quantify. If Quantify goes down, we go down with it. Yeah. Does that answer the question?
It does. Thanks. And maybe one follow-up. We have seen that Qiskit or IBM introduced like those functions, like the App Store for quantum computing. Have you thought about introducing something like that into your platform in the, let's say, far future?
Yeah, we've thought about that. I think it's an interesting idea to try to make something tangible, at least for people who are less technical as the rest of us. So yeah, I think we're thinking about that, but yes, in the far off future. Yeah.
Okay, thanks. Great work.
Thank you.
Any further questions? Yes, one more.
Thank you for the great presentation. So I noticed you were using OpenPulse, and well, from what I read right now, it is a more human readable version. But that does also mean that the circuit you submit will be larger. So how are you planning on dealing with very large circuits that will that the instructions may be much larger than, for example, you would expect. Like, I don't know, is the size of a circuit a problem for you in the testing stage or in the future? How are you looking at this?
So that's a great point. We still experimental, so we have not yet run into those issues, but that's something we're trying to think about. We don't have an actual solution right now. I mean, I'm guessing it would also affect the bandwidth and the like. We'll probably find a solution. Do you have a solution you have in mind?
I mean, probably just have an open pulse to some only machine readable format that should probably compress it, but that is something that I remember in UnityCon, for example, that was in Helsinki in September. They were really discussing this, especially because OpenChasm 3 has a lot of features, so it's become a bit bloated. And so instruction sets are getting larger and larger.
Yeah. Just like I think ESKit, I think ESKit was compiling it down to some binary form, the new version. That's what I had, but okay. Okay, thank you.
All right, let's thank Martin again. And let's invite the last speaker of the entire Quantum Autumn School.
Yeah, thank you very much also for the opportunity to do this. And I've noticed that I'm the last speaker of today, so you want to be going home or doing something else. So I have to refresh you a little bit for that. Who was in Iceland already from you? Nobody? In the Nordic? Yeah, well, Heyman does, I know, and you have been to Iceland. Very well. Okay, I brought you some lava, right? So in case you have never seen the volcano, because we switched on the volcano right now at the airport to attract more tourism, I brought you also some lava. Right, I have the opportunity to talk you a little bit about quantum activities, and we have quite some of them, although we have to also admit that we collaborate really a lot with Germany. That's why you see also there the German flag and the center called Jülich Supercomputing Center. Some of you have maybe heard we're getting the first exascale system in Europe very soon, but we do also a lot of Icelandic and studies with Germany together. So I'm the head of the EuroCC 2 National Competence Center. So I thought I'd just briefly introduce you to that. Basically, I guess you have started the events of introducing ENCCS. So I will not need to introduce the network as such. We are just the Icelandic part of it. So competencies, mapping them, where are the experts in the country. We do lots of events. You see there, we have already 18 EHPC workshops. And for us, the project was quite essential because in 3 years, 4 years ago, there was just an EHPC mailing list. Nothing was happening in HPC, basically. A couple of groups like Hannes, leveraging HPC, but no community, no really visibility. Hence, what we have done since then is coming to something we call application domain-specific application labs, which are dealing with simulation and data. So we call them simulation and data labs. And you see many of them here and have not the time to go on all of them. We also collaborate a lot with industry. You see here 2 testimonials working with industry. I just mentioned them because also it has some relevance for Sweden here. Ms. Linköping as the coordinator of TrustLM and working a lot with AI Sweden, for instance, just to make some connections, possibly also with AI factories maybe in the future. You have heard already from Heyman, maybe he's still there. I guess he's the leader of our quantum lab, so doing there already teaching like quantum cryptography is in our curricula. We're quite university-based, so we're the only partner in this National Competence Center. And not all of these different application-specific labs have really, let's say, quantum experience. So I will highlight those which already have done lots of work on quantum computers. Before I just go there, we are also active in lots of EU projects. Again, TrustLM here is for us a very important technology where we work on to have a large language model on Icelandic because we're a low resource language, but this is basically shared with many of the Nordic countries except Finland. They have, of course, a complete different, not Germanic character. And you see how that works with the simulation and data labs. We have different people there, different competencies, the experts for all of these different, let's say, application-specific domains. And this is for us very important because that's why we also believe we can make a difference in these different application areas. For us, this project was quite a success, also from the National Competence Center. That's why I mentioned it. It was quite instrumental bringing this proposal together. We started with a German-Icelandic, let's say, connection, and then we entered Linköping, AI Sweden, and many others in the Nordics together. Hence, we got it. The Horizon project, which is quite nice, basically for an Icelandic company, 2 people, and 2 people also for the university. Now coming a bit more to quantum, we did this before with another project called CEU RACE. That's where basically the quantum activity started in Iceland, I would say 3-4 years ago when we created the proposal. Again, we see very nicely how that works with EuroCC, bringing the competencies together. We combined the power of different application labs here. These SDLs are quite instrumental with the expertise, so remote sensing, acoustics, and also computational fluid dynamics, and applied for a CEU RACE project and also got the Center of Excellence. Now they have different use cases and I have not the time to go all in of them, but the important thing is that this was the first time where also then Icelandic students started to use unique, the basically Jülich infrastructure for the new quantum computers. It's basically known for having one, which is a D-Wave systems that we basically have there on real life quantum computing. And this is the outcome of RACE. Many of these things are not really relevant to you. Some has been mentioned with LAMEC, I think from Heimann, make it easier for job scripts. And we try to push that as well, possibly integrate together with Colony OS, as we heard. But for us, it's important to have also this D-Wave quantum annealing as one of the future systems for being more resource aware. Now, RACE was also focusing a lot of AI, and for us, one of the major benefits was the hyperparameter tuning, so RayTune, Optuna. We were using this a lot, and with this, also lots of HPC resources, because machine learning accuracy usually relies in how to pick, properly the hyperparameters. Hence, we were interested in the quantum study to explore that. And you see here again in the Icelandic Student Innovation Fund, we have been twice successful by cooperating with Jülich, giving Icelandic students an access to these to these quantum computers that are really, in our case, really modular. So we basically have heard maybe in LinkedIn or so, we just got a quantum simulator from Pascal as well. We have the Advantage system with 5,000 qubits. And it was, of course, for Iceland a really nice, let's say, possibility that these students really can access a quantum device. And we did lots of studies. So one of the ideas really on this system to have around 5,600 qubits there. But, also the computing time, that's why I was mentioning as one of the questions, is like this, right? While we stochastic gradient descent, we do iterative machine learning, optimization, yada, yada, epochs by epochs. So for us, the solution or time to solution is also relevant, accuracy and mean square error as well. But still, this is also for us a very important factor. Hence, when we use this machine, we tried a study together also with CERN in the CEU RACE project, where we used the quantum annealer together with a classical HPC, let's say, approach, trained a neural network, and the epochs that we could see in the error rates and to basically predict what will happen in the next couple of epochs is something we outperformed on the quantum annealer to get some idea of what of these runs, when you do hyperparameter optimization, have a better chance of success, right? There are different algorithms doing this hyperparameter optimization at scale. Of course, the details are in our journal paper there that is basically published already. But the idea is really using these best systems together. I have no time for the whole paper presentation. Obviously, I just wanted to point out that really when you do it in the hybrid solver here, we got the best, let's say, performance ratio. Of course, the loss in the normal hyperband was better, in the end, but you see the resources we spent, the compute resources were much, much higher, right? So the end, this Swift hyperband with having, let's say, very, very little resources used is, of course, then an interesting approach for us. It's still like support vector regression and quantum is still new, so there's definitely room for improvement. But it was a first study which is quite nice and shows interesting result, especially as the time to solution is so, let's say, low. That is something what we did with the SDL, so the simulation data-led software engineering and quantum computing activities. But I also would like to give you the pointer to our remote sensing quantum computing activities. They're extremely active in this, working together also with ESA. So you see Amer, one of my PhD students, and the second professor we have in Jülich and in Iceland, Gabriel Cavallaro there. They are also basically at the same time as some ESA lab, right? The European Space Agency. It's a bit problematic for Iceland. We are not part, basically, and cannot take part of ESA. But through the Jülich link, we have the possibilities that student of us, of course, can also be part of ESA. And they do many publications. You see here one which is very recently and also available to you, a multi-class support vector machine, which is a quite nice approach for classification. Still, of course, from the data side, we usually have satellite data in the orders of terabytes, gigabytes, and so on. Here we boil down the problems, right? So we're not there yet in high performance computing. But I leave you with these publications and this team that is also organizing summer schools, actually, every year in Iceland and also in Spain. It's called High Performance and Distributed Computing and Disruptive Computing Approaches, where quantum sessions are always basically also part of it. I also mentioned the ESA study. For some of you, may be quite nice to look at, which we have done together with company IQM, I think was also here taking part, but also some other players, where Iceland was basically indirectly involved with the right players. Another paper about kernel approximation. If you know a little bit of support vector machine, they're using this kernel trick, right, to basically have good performance. And one of the students from me there, Eduardo Passetto, and so on, we working on this as well. And this is something what we also give to the community. Of course, it's a quantum annealing SVM, right? So this is different. And maybe then just more on the let's say things to come and what we do with the Icelandic government. We also provided reports to the Ministry of Higher Education, Science and Innovation, with the idea that we basically have quantum computing research activities in Iceland. They were quite surprised. They didn't know that we exist. Of course, we have to always brief them, the politicians, that there's something happening in Iceland, and it's something what we continuously do. Just recently, we gave a presentation as well around AI factories, what we do in HPC, machine learning, and quantum. So that's something for us very important, and also maybe open doors for cooperation in the future. That's why I also mentioning here in the Nordic section, where we probably have more and more things to come together. Then finally, our students already look forward to use the Pascal system that was just delivered in Jülich. I cannot show anything about it. It's about 100 qubit, but a simulated one. And then maybe I should finally also point you to the EuroHPC user days, which are happening also in the Nordics in Denmark. Just save the date. That would be an important part here, being also the EuroHPC governing board member of Iceland. To not take too much time from you, because we had long sessions. You had long sessions. I came a bit later. I apologize. Thank you again for the invitation, some references, testimonials about companies. It's normally relevant in EuroCC, not so much here in quantum, I guess. That's a team I should still mention. Many of them dive into quantum extremely these days, like Amer, Deli Basic, and of course, contact us, please, if you want to have contact to these people or those that use Pascal. So thank you very much.